Yeah.
Kevin, if you want, you can try that.
Okay, now I get it. 1, 2, 3. What do you see?
Yeah.
Do you see the?
That's right. We
presentation?
can see that.
I think that's right.
Yeah, we can see your presentation. First slide. Yeah.
Okay, now stop share.
Yeah.
Okay, it's all good. I get it.
All good. Yeah.
What time are we getting going? Oh, can hear you.
Hello and welcome to International Geoscience Colloquium, jointly organized by Christ College Autonomous Irunalakuda, University of Kerala, University of Exeter, UK, and University of Zululand, South Africa, supported by Ministry of Earth Science. I'm sure you all are eagerly waiting for today's session, and our session will be on developments in stratigraphy and sedimentology, big data analytics and artificial intelligence in geosciences, geoscience and integrated reservoir modeling. And let me now invite our session chairs, Dr. Saju Menacheri, sedimentologist, reservoir quality geoscience, Georeservoir Solutions, Perth, Australia. Dr. Linto Alapart, head of the Department of Geology and Environmental Science, Christ College Autonomous, and Professor Vetrimurugan Elumalai, professor from University of Zululand. So Dr. Saju Menacheri, can you please take over the session now?
Dr. Saju, could you please unmute?
Yeah, thank you. So welcome to the virtual International Geoscience Colloquium Session 3. My name is Saju Menacheri, together with Lindo Alapat and Vetrimurugan Elumalai. We are the session chairs for the technical session 3, development in stratigraphy and sedimentology, big data analytics and artificial intelligence in geosciences, geosciences and integrated reservoir modeling. In this session, we will be having around 5 presentations covering the various aspects of the topic. Each presentation will be around 30 to 40 minutes. At the end of each presentation, you will have 10 minutes question and answers time with the speaker. The first session, this session is a geoscience and integrated reservoir modeling session. I would like to introduce you our first speaker today, Mohammed Al Khalifa. He's from Saudi Arabia. He will be presenting on the subject on subsurface reservoirs imaging through characterization and 3D modeling. Dr. Mohammed has more than 20 years of experience in building 3D geological models and reservoir characterization, as well as integrated reservoir characterization and field development. Currently, he is engaged in technical talent development and mentorship programs. He holds BSc and MSc in geology from King Fahd University of Petroleum and Minerals in Saudi Arabia, and PhD from University of Adelaide, Australia. I would like to request you all to mute your video and microphone all the time until you have time to ask the questions during your question and answers. Please enter any questions you may have in Q&A chat box in right corner. You may enter a question during the presentation. You don't need to wait until the end of your session to enter your question. So please welcome Dr. Mohammed for the talk.
All right, good afternoon all, and good morning for whatever your time zone. I would like first to thank the committee for inviting me, and thank Dr. Saju for his invitation, and all the good friend of mine. We spent good days in Adelaide in Australia but I might be still there. And I would like just to share the screen to set up my presentation. It always give me a great pleasure to talk to audience, a diverse audience, about subsurface reservoir imaging and characterization and modeling. My talk first, it will have focus on 3D geological modeling and how we do that, what are the geoscience aspect of it. Second part, I will focus more on the topic also of this event, which is data analytics, artificial intelligence, and how we as geoscientists prepare ourselves and the next generation to meet this requirement. With that, I would like to start to set up the big picture. So we'll talk about reservoir modeling and simulation. And my talk today in presentation is about the geological model. Geological modeling has a wide range of application, from groundwater to, again, to in the oil industry and the environment and so many. But today in my presentation, I'll be focusing on how we build subsurface geological models with a focus on oil and gas industry. The geological model, it's important. It's a factor, or it's a big input in the economical development of a field. So the geoscientists working with petroleum engineer, they will develop a geological model. Let me just switch to the laser. So at least that's so. So this is our ultimate product, a geological model that encompasses all static data from the subsurface, that structure geology, seismic, logs, core, and all of that will go into reservoir simulation for a fluid flow. Here where reservoir simulation utilize the production data from the field, tweak the parameters, mainly permeability, change the pressure parameters to match the real data, develop a best match, and then use it to predict future performance. Depending on how big is the oil reservoir, the decisions here ranges from hundreds of millions to a couple billions of dollars. And it all depends on the accuracy of the geological model. And as probably all of you know, junk in equals junk out. And you don't want junk out for decisions that are hundreds of millions of dollars. So today, I will take you on a short journey how we build a geological model. I will focus a lot on the importance of sequence stratigraphy, as it is the main tool that we depend on to build an accurate models. This cartoon represents the subsurface. It's important to note that the information of the subsurface that we have comes to us through drilling a well or acquiring seismic data. And there will be a detailed presentation following me on the application of geophysics, and which is great, that will fill a big important picture of how to characterize the subsurface. And for us, we drill either a conventional reservoirs, such as this one, this example, or sometimes we drill for unconventional reservoirs or a tight gas. So all of these we can develop subsurface geological models. My area of expertise has been always in reservoir characterization and modeling of conventional reservoirs, and the same principle can be applied to the unconventional reservoirs, more or less. With that, I would like to introduce a few concepts at the beginning. It's 1D. It's the data that we have comes in different dimension. We'll be talking about 1D. 1D is the data that come from well data. And this is where we have our highest accuracy and least uncertainty. Most of this data come either from the core, the piece of rock that we cut from the reservoir, or through the log data. The second is the 2D. And the two-dimensional that we refer to is the studies we do in the field, where we go to an outcrop and measure a stratigraphic section, observe the faults as they appear on the surface, or create a cross-section from wells that are drilled, or a 2D maps, or a cross-section in seismic cube, or a 2D seismic. As we move from one-dimensional to the two-dimensional, our uncertainty will increase, with the exception of the outcrop. The outcrop is the real data. So basically, still we have very high accuracy and least uncertainty. But in all other, our certainty will increase as we move from 1D to 2D. Third is the three-dimensional. And this is in reality where we have most uncertain. Three-dimensional could be the systematic depositional model. It could be even the inversion of a seismic cube, or it could be the 3D geological model. We're moving from a one-dimensional model where we have most of our data until a 3D. The magnitude of the uncertainty will multiply significantly. Therefore, we need really to focus more on how we acquire the data, ensure our data is precise, representative, and because any error in here will multiply significantly in the subsequent steps. With that, I would like to show you a 16-cell matrix where different disciplines and different data, they come together. And the sources of data that we have are the core, the log, the seismic, and the dynamic data. The disciplines involved: reservoir stratigraphy, reservoir structure, reservoir properties, and reservoir field operation. All of them are horizontal except the seismic, where the seismic crosses the different disciplines, and that highlights the integration. It's very important to highlight we work in a multi-integrated environment. Geological modelers work with all of the cells in this matrix. That means he or she need to work very closely with the geophysicist, stratigrapher, the structure geologist, the petrophysicist, as well as the field operation, and capitalize on them. Now, I will talk about the sciences that utilized heavily in the geological modeling: sequence stratigraphy, structure geology, reservoir geophysics, petrophysics, and geostatistic modeling. As you can see, we work on a continuous loop. A model is not complete as long as we acquiring data, the field is under production. There's a lot of data that comes in, and it all need to be integrated in a cycle type. If we get a seismic new sequence stratigraphy that we need to incorporate, some cases we get a new petrophysical analysis that require us to update the model. From a bigger picture perspective, it would seem that the team members in the integrated model are working separately. We're doing their own tasks. Sequence stratigrapher working on setting the sedimentological stacking patterns, doing their stratigraphic cross-section, working on their facies prediction until they come up with a stratigraphic model. Structural geologists could be working on the seismic interpretation, go into the field, the geophysical reservoir characterization. This is one of the long leading item. They will acquire the seismic, process it, converge it, QC it until it becomes in a stage where they can start to put the wells, make sure that they match the depth and do their own interpretation. Meanwhile, the petrophysicist working on their appears to be working on their logs. So if you take a look, I look back, it would seem that everybody working in their own domain until they produce the hydrocarbon in place, where again that will go to the reserve calculation and so on. So this will seem as parallel tasks going through time. In reality, that's not the case. We work in a multidisciplinary environment. Again, this is a quick legend to what are the model types are 1D, that mean work that's been done at a well level. 2D is a cross-sectional, and 3D is a 3D model. And the arrows highlight the products that come from each task and the input revision. In reality, the stratigrapher is working continuously in iterative loop. Also, they interact with the structural geologist and the geophysicist. The geophysicist work a lot with the structure geologist. And again, the petrophysicist is deeply involved in this. So the team work together. Every model that comes, the first model we generate, where it will be the box that has the property distributed, is that we call the structural model. The structural model, it will have the sequence boundaries, it will have the faults, the major lineaments. It highlights the major pipes of the system, how the big bodies of the system connected. The second layer will come on top of that, is how the facies bodies are distributed. And where is the good reservoir interval lies, and the low permeability, low porosity, any permeability barriers, any high flow, all of these are controlled by distribution of the facies within the sequence boundaries, the faults, and major structural elements. When these two are done, this is in a way, it's building a house. You build the foundation, you have your first floor, second floor, you already divided the rooms, you establish everything, you make sure of the structure integrity. Then the property modeling is where you distribute the porosity, the permeability, and the saturation. This is where you go to each room and you decide what color I'll paint it, what properties I'll put there. And when you're done with all of that, then you compute the hydrocarbon in place. This is give you the economical value of the field. This number has significant impact. As most of you will recall, oil prices at one point of time was $75. It went down to, now it's around 40. So based on this number and the oil prices, the field could be economical, where you invest hundreds of millions of dollars or billions to develop it, or it could be uneconomical, where you will freeze it on the side until either technology improves to reduce your cost, or oil prices goes up and the field became commercial. So the message to take away from this, the geological modeling is an integrated process. All the team players, they should work together to produce a result. The result is, the ultimate is the economical value of this field. Should it go to a production, or should it be shelved until the condition, economical technology becomes better? So now I will take you through a quick journey through the science of the geoscience aspect of reservoir characterization and modeling. And I will start first with the sequence stratigraphy. Now, I mentioned the direct source of the subsurface reservoir is the core. And there is where there's a special drilling bit that is hollow inside. We go to the inside the reservoir, and we cut a piece of the rocks, bring it to the surface. This process is expensive. Usually only 10% of the wells drilled in a field are cored. And usually wells are cored at the beginning stages of the field. And that's the discovery and appraisal. As the field goes to development, the percentage of coring reduces due to economical reasons, which makes this is a very crucial, very important piece of information. And this is the most representative direct piece of rock. It is analyzed extensively. This is an example for a core description, if it's for carbonate. And this is another example for a clastic reservoir. One of the most important QC part, because we need to match the logs with the core data. Remember, 10 to maybe 15% of wells are cored, while up to 100% of the wells are logged. A match between the core and the log will help us a lot to understand the subsurface reservoir. A common practice is to ensure that the core depth is matching the log. Remember, as we acquire the logs, we acquire them through a string. It's a wire line. While we acquire the logs, we acquire them through a drill pipe. Depending on the depth of the reservoir, there will be a couple of feet to 20 feet, or again, few meters difference. These few meters in difference will offset all the core properties. And therefore, what we do a core depth shift, where we try, if we have a gamma ray, for example, we run a gamma ray in the core, we match it to the gamma ray of the log, and we match the section to make sure. And this is only to highlight that through our work, QCing, checking the data is a continuous process. Never take anything for guarantee, and especially working at 1D. The more time you invest in QCing the data, ensuring the quality is a time well invested. Another thing that we do is visiting the outcrop. As I mentioned earlier, coring is expensive, but the reservoirs, most of the cases, they will have an outcrop or a similar analog. There is no substitute to visiting the outcrop, looking at the rocks, studying the sequence boundaries, and looking at features that may not be observed through the logs, coring, or even the seismic. And this is again an example. This is the scale is 10 meter, and there are some local heterogeneity. So here's some rework channels that are filled by coral heads. The chances of drilling a well in these is really slim. Depending on where you are in the world, the distance between the wells sometimes 500 meters, and some cases few kilometers. The chances of hitting a feature that is 5 meters in length in a field that the well distance, the distance between the wells, the kilo, is very close to zero. However, even though they are small, during the history of the production of the field, these will contribute to the flow and may cause hypermobility layers that will be difficult to understand. Why is this happening? Without understanding this, exists because the geophysicist will image the reservoir, and they can image it at a high resolution, but there are some features that are below the seismic resolution. And this is where the importance of going to the field, looking at the data, checking some irregularities, some features that may be even beyond the log, resolution. And then it will be our responsibility to say, how can we fit this feature that's 1 meter into the model? Depending on your model size, some model cells are larger than 1 meter. Some cells may be less than 1 meter. But this is part of a decision that the team has to discuss together and incorporate in the model. What's also another importance to understand, what is the depositional setting of the reservoir during at the time of deposition? If you're working on a reservoir that's 50 or 100 million years, probably right now it's a different structural setting, diagenetic setting at the time it was deposited. It's important to reverse the clock, understand from the data that you have, how was the reservoir deposited? And at time of deposition, where was the good part of the reservoir? Where were the low priority of the reservoir? And when you build a model, you try to take these facts in your consideration, because there will be a lot of gaps. You need to fill these gaps based on geological knowledge. And it's important to note that to not let the statistical algorithm do the science. The algorithm responsibility is to generate an image of the reservoir that you as a geoscientist has developed in your mind. And you can check the QC the quality, revise it until it matches your understanding. Now you might ask a question: if we core only 10% of the wells, how we predict the facies for the 90% of the wells? And that's a process, what we call facies prediction, where we rely on the core. We make sure that the core matches the log signature, and that goes back why we need to ensure the depth match between the log and the core. And then we use algorithms to predict the facies in uncored wells. As I do expect, different algorithms will give you different percentages. For example, this is the same cored wells, and we try to predict using different algorithms, and the success ratio was let's say 49 to 77. So we know the core, and we gave the log to a trained neural network algorithm, did not use this core. And we asked the algorithm to predict the core based on a number of a training data set with core data. And we went back and we compared what the actual core and with the algorithm. The range of error is huge. It could be 49, it could be up to 77 of accuracy. Now, we know this. So it's a well where we have a core. Now, imagine if we don't have a well, we don't have a core for that well. This is why I said the uncertainty will start to increase away as you go from 1D to 2D. Imagine 90% of the wells that you have in the field, and you do not have really a direct measure or a reliable measure of uncertainty, and you build a geological model. If your geological model is off 50%, that's a huge consequences on it. Therefore, we do not rely only on the facies. We need to use other data to reduce our uncertainty. So now I'll go more talk about the structural geology. Again, the structural geology, there are two components. There's the macro structural geology, and this is where we rely on the seismic interpretation to get the faults and the horizons. And this is, again, a very simple systematic process. We tie the wavelet to the log. We convert the depth to time. The seismic is in two-way time. We do our own interpretation in the time cube, generate isobax maps, check it doesn't make geological sense. For example, here are the fault boundaries. As you can see, the fault boundaries coincide with sharp change in thickness, which we interpret as there were some growth events. So this area, the growth has erosion. Areas did not have any growth, did not have any erosion, which again, all of this is a QC to build confidence in our interpretations. Second is where is the micro, and this is considering looking at the formation image logs, doing the interpretation, and looking at the connectivity of this fracture, permeability, stress regime. Here I'll highlight two types of fractures. One are layer-bound fractures and fracture that cut through boundaries. The importance of these fractures will not carry fluids from other. So if this is a hydrocarbon zone and this is a water zone, I can drill a horizontal wall and I will be confident that there is low chance of water coming from this zone. But in this case, where the fractures cut multiple layers, if this is a water zone and this is a hydrocarbon zone, I need to think of a different way. I cannot drill the horizontal this way. I need maybe to drill the horizontal inside the bed, where I need to avoid intersecting the fractures, to avoid getting. And all of this data will be part of the model. It will be included as part of our geological model. One of the things we do is to distribute the fractures. And let me just go back. There are the fractures we're highly confident with that we see from the log. These tend to be low density. A higher density fracture that come from the seismic interpretation. And there will be some stochastic fractures that we introduce in the system based on the regional stress, based on some geophysical studies. And these are important to introduce some factors that may contribute to the fluid flow other than the matrix. As you would know, the flow in the reservoir will come from two sources. First, there's a flow from the matrix, the reservoir rocks itself, and second will be from the fracture. Depending on the fracture intensity, with high fracture intensity, the flow from the fracture will dominate the flow of the reservoir. And in some reservoirs where there's very low fractures, and there's the most dominant mechanism is the matrix fluid flow. Therefore, as type of our uncertainty, we need to make sure that we consider wide range of cases. So when we go to reservoir simulation and they observe high flow, then they can relate it to the fracture. If it is low flow, it could be there's no fracture, then we use low density of fractures. Now, I will not touch much more about the geophysics. It's not my area, but geophysics is a very fascinating science. The process of geophysics starts with acquiring a seismic. Although this may seem a simple process, you send a wave and you receive a wave and you receive it on the surface. As the wave goes through the surface, it will refract or reflect, and there's a crew at the surface. They will record it. This is a very important process. The accuracy of this, it's really very important. Any small error in the arrival and recording the time of arrival will give you a totally different image of a subsurface. Therefore, at least the crews, they spend a lot of time in setting the arrays, checking the equipment, QCing the data. Because when you acquire a seismic data, it's not easy to go back and acquire it. And this is, again, a very expensive process. As you can see, this is on the land. Seismic data is acquired in the sea by ships, which again is more expensive. And, the seismic, again, it has its own 1D, one-dimensional modeling, two-dimensional modeling, and three-dimensional modeling. Again, I will leave it to the next presentation to share more about this. It's not my area. Now I'll touch more about the petrophysics. The petrophysics, it deals with what type of fluids we have in the reservoir. When the reservoir rock were deposited at original time, all reservoir rocks are filled by water. As the reservoir subsides, still it will carry the water inside it. As hydrocarbon migrates from the source rock to reservoir rocks, the hydrocarbon will replace the water, some of the water, not all of the water. There are cases where the first migration will be oil, second migration is gas, so you will end up with gas, oil, and water. In petrophysics, it is the study of the reservoir fluids. How much gas we have, what is the gas and water contact, or gas and oil contact, how much oil we have, what is the oil and water contact, and the lithology of the rocks. And from that, they develop equations that will help us distribute the saturation, the permeability, and the porosity between the walls. Also, they provide us with a measure of uncertainty that we can utilize to gauge what is the uncertainty or the possible ranges in our hydrocarbon place. And with that, we can utilize in the economical decision and studies. With that, I will touch briefly on geostatistics. Geostatistics is a branch of statistics that deal with correlatable data, and this is at least the geology is especially correlated. Now, the sequence of building a geological model start with building the structural framework. This is where we integrate the structural data, formation types, faults, fractures, with a stratigraphic interpretation. Within that, we build a depositional model. Very important, we model the phases at the time of deposition. Should there be diagenesis, then the diagenesis will come as a second layer. And this is an example. This is anhydrite. You can see this is the basin ward, and these are the grainstones. You can see the grainstones are migrating through time and space. Within that, we build a porosity model controlled by the facies trend. So as we move from here to there, you can see immediately that the uncertainty is increasing with us. Therefore, we need to have a measure of how much of error we might have, consider how much error we might have, and also as well how much error we have. And if you look at this porosity model, you can look that the lighter colors correspond to the good reservoir phases. Darker color correspond to the low reservoir quality parts. With that, we use the porosity converted to, again, permeability model, which is more of petrophysical data integration, until we come out with a saturation model. And what saturation tell us? It will tell us areas where we have hydrocarbon. These are the areas where we drill wells to produce. So if you look at this, we build this huge model. But if we want to place a well, we can place it only in this interval. We need to build all of this to account for all of different parameters impacting the geological model until we come up with a much smaller area that we can drill. So in reality, this model, this is where is the hydrocarbon, and all the blue is either non-reservoir or it has water. Again, I took you through the first part. I focused a lot about the geological model, and I hope that I gave you some aspects of the uncertainty and the impact of this geological model in the decision-making process, how this geological model fits within any upstream company, oil or gas, conventional, and how much significant of this. This is why we need to rely on the geoscience, give it the best knowledge that we have, try to be as accurate and precise as much as possible to reduce the uncertainty and help in coming up with a future reservoir performance. Now I would like to touch on the second part of my presentation, and the recent industry, the talk about big data and artificial intelligence. And as a community of geoscientists, we always face with the questions, what is our role in the future? How can we prepare the next generation? And one part of the geology specifically is going to the field. So everywhere we talk about geologists, everybody think this is the image they have. We go to the field, we take rocks, break them with hammer, and the new generation think, well, now should be the new, everything should be virtual displays, it's high machines, and we should be all moving to here. Actually, we should have both. We need to have this side with this side. We're now at a stage, it's not either or. We are in a stage where it's integration, where we need to build on what's really there. There's no substitute going to the field. At the same time, there is no substitute for using the new technology. There's a lot of talk about the big data and the analytics, and this is true. They will change the EMB landscape, exploration producing. There's a new products and services coming out every day. And how we deal with this? To deal with what will come in the future, we need to look at the past. And this is a very rough look at how the oil industry started. This is how they used to drill the wells with the handheld rig. And it moved to a rig platform where the rig, it's not dismantled. And these are old images. Some of them they're still there. This is how they used to drill in the offshore. But look how drilling technology has changed. They stepped to the deeper offshore. Now, everything is run by satellites. In one room, you can control production of hundreds of thousands of barrels or even millions of barrels through a network that's automated. One room, you can decide which well to produce, which well not to produce out of 1,000 wells. It's amazing how the visualization right now. I remember when I started, seismic interpretation was done on a piece of paper. Now, everything is done digitally. How to prepare to this? We need to continue developing the geoscience that we have, sequence stratigraphy, structural geology, reservoir geophysics, petrophysics. These are must. These will never go away. What we need now to include with them is a quantitative skill set, more involved in statistics and probability, understand what is experimental design, build mathematics and modeling simulation, where we again build our skill set in different areas. And these are the requirement to do any data analytics. The more you understand statistical probability and experimental design, how things work together, this will help us to capitalize on what's coming next in the data analytics and so on. I would like to conclude with geoscience is a very fascinating specialty. I've been working on it for the past 20 years, and I'm looking forward to continue working on this. I never had a boring day. Every day is a new day, and it's an interesting day. There's a lot of career and opportunities for geoscientists. If you are in university, there's a lot of jobs waiting for you. If you're currently in a job, there's a lot of opportunity to grow in the job. Learning is very important. Reading, writing, and presenting. One of them is attending such events as we discussed today and we were talking about today. Keep doing this. This is a message for my colleagues who are just starting, or their mid-career, or even at a senior stage of their career. We need to learn, write, and present, and be prepared for whatever comes in the future. Thank you. I really had this is a great opportunity for me to present. And thank you for the committee for inviting me. And if you have any questions, any comments, please let me know.
Thank you, Mohammed. Now it's the time for any questions. If anyone wants to ask any question with Mohammed, please unmute your microphone and ask, or you can write on the chat box. We can read for him. If there is no one asking any question, I would like to ask the first question. When you mention about like looking from your sedimentology or stratigraphy as a start point of your model, and to made or the first model you come up with, what's the time duration usually take?
All right, that's a very good question. It will depend on the data that we have. And if it's let's say you work on in a field with 100 wells, and most likely we'll have up to 15 cores. I'm not advocating that first you describe the 15 cores. No, describe 10. Depends on the length of the core. Visit the field. That will usually be done in 1 year time, where you build your first initial depositional model, your understanding of the subsurface. Then with that, you back test it or validate it with the 10 wells that you drilled, that you did not describe before. So within 1 year and a half, you should have a good understanding based on the core only. Then next step is to validate it with the geophysicist, see what they have, put a structural component in it, understanding of how the basin was formed, what was the shape of the basin during the position of the reservoir, and after. That will give you another. It's important to know that 1 year and a half will give you your starting point and understanding the rational model. You will continue to refine as more data arrives.
Yeah, that's a good answer. Like, I mean, that's most of people looking to see what usual time it happens. There's another question typed on a chat box from Justin Rajani. He asking, I would like to ask if you are considering the biomarker data to build your model, especially to find out the migration, etc.
The biochemistry from the chemistry, or?
Yeah, biomarker. Like, I mean, maybe he's thinking of biostratigraphy to sonation or that.
All of these are very important. And again, when we build the big picture, you continue to validate. Let's say if the biostratigraphy comes and matches the data, that's great. If they contradict, that's even better. At least you have a different perspective. You try to find what are the differences. Now, What's important is in the biodata, one of the issues usually we are facing is how it's sampled. If it is sampled from the cuttings, sometimes there is a depth shift in the cuttings. And it could be a considerable depth shift. If the biodata were collected from the cores, then that's great. Then you are already matching what the core has. And again, I haven't touched on the lithography and the thin section, but all of this play a big role. It's an integrated process. You look at the data from the micro to the macro as we go.
Thank you very much for that clarification and good summary. Is there any other question to ask? Because I mean, we are approaching to the time limit. So maybe one more question from anyone?
Mohammed, that was a wonderful presentation. Thank you so much. It was given very sequential order for students to understand it very well. And the last point, what I got from your presentation was that geoscience is not the science that we had studied in the past. Now it has turned to something totally techy and new. So what would be your advice for the upcoming geologists? Because I see that many of our students here. So what they should be concentrating on, mostly on the science part, or rather they should also understand more into the modeling. So what would be your pick for the students?
In university, while you're in university, capitalize on the opportunity to go and see the rocks. Because as you go to, and if you work in, again, an oil company, oil and gas company, one of the things that you will miss a lot is going to the field. Most of your work will be in the office unless you've been assigned to work in the field. So the sequence stratigraphy, structural geology, reservoir geophysics, these are taught in university. Spend a lot of time building strength on these. Petrophysics is by itself is a discipline that's developed in the industry. While you also in university, there's a lot of room to develop skills in statistics, experimental design, mathematical modeling, and simulation techniques. Of course, computer coding with the new generation, use of Python and other softwares, they already have it. So, but do not jeopardize your learning in the fundamentals. It's amazing when I reflect back again. I had Seju and myself, we had a great professor. He was sequence stratigrapher, and he will go to the field a lot. And now I regret I haven't went with him to the field as much as I should be. But university offer you a chance, a rare opportunity to strengthen your fundamentals. As you move to your career, in the job you're expected to produce, you will have deadlines. If you do not build your science foundation in university during your bachelor or master or PhD, you may not be able to catch up in the industry. This is why I stress on the last point. Success requires long life learning, reading, write, and present. In university, you will have a lot of time to read and write and present. In the industry, the time to read and write and present will not be during office hours. It will be when you come back at home. And then you need to balance your family life with your development, with your business. And you rely that on the job, they will also require you to work even after working hours. So capitalize on any learning opportunity, whether you're a university or you're on a job or you attend these events. These events are really crucial to develop. And now with the virtual delivery, you can reach anybody internationally and you can learn from them. I hope that answered you.
Thank you very much. That's very nice answer that a student can take up. That's wonderful. Thank you.
Thank you very much, Mohammed. It was a great one. And thank you very much for your the entire presentation and the answers.
Thank you. Thank you very much.
We have one more question. I see it in the chat box.
Because of the time, can we go for the next presenter? Could you please introduce the next presenter?
No problem. That's fine. Okay, am I audible now?
Yep.
Okay, so that was nice presentation we had. Now we have the second presentation. So I would like to introduce to you our second speaker today, Dr. Kevin Jarvis from Australia. He's a senior petrophysicist from Perth, based geophysical consultant. He will be presenting on the subject, the application of seismic methods to characterize the subsurface of the Earth. To give us a few words about Dr. Jarvis, he has graduated in 1986 with a Bachelor's of Engineering Geophysics from University of Saskatchewan from Canada. 6 years as an exploration geophysicist with Chevron Canada in Calgary. MSc and PhD in geophysics at the University of British Columbia in Vancouver, Canada, and specialized in laboratory rock property measurements and near-surface seismic acquisition, processing, and interpretation, primarily in P-wave and S-wave. A consultant geophysicist based in Vancouver, Canada, for 5 years working on various projects for mining and engineering companies. He has 18 years of reservoir characterization project experience with Fugro, INPEX, and Chevron, involving project execution, employee mentoring, and training. He has completed seismic inversion and interpretation project all over the Asia Pacific, from India to New Zealand to Japan and most of the petroleum basins within and around Australia. A key focus area of his expertise was improving the use of seismic reflection data for the constraint of reservoir models. His personal interests include ice hockey, cycling, and scuba diving. So with this brief introduction, may I invite Dr. Kevin Jarvis for his presentation. Over to you, sir.
Okay, can you hear me clearly?
Yes.
Yes.
Okay, I'll share my screen here. Okay, so you should be looking at the presentation on your screen.
Correct.
Okay, that's good. Okay, well, welcome everyone, and thank you for giving me the opportunity to present at your colloquium. The purpose of my presentation is to discuss basic seismic methods and how they can be used to obtain rock property information in the subsurface. So here's a general outline of my talk. So I'm going to start from basic seismic principles, and hopefully this is not too simple, but I'll start from the beginning. And then I'm going to show some examples both in the near surface as well as deeper offshore for gas reservoirs in Australia. I'll then discuss and show results from seismic inversion and finally draw some conclusions. So obtaining rock properties of the subsurface in a traditional sense involves putting a hole in the earth and then taking measurements or samples from that hole. The cone penetrometer, which is shown on the left in the figure, is a fast and cost-effective technique for unconsolidated sediments, such as geotechnical near-surface applications, whereas drill rigs are used for harder materials and capable of much greater depths. The seismic method, well, what is it? This involves the propagation of shear or compressional waves through the rock, recording the data at a set of receivers, and then processing the resultant signals into images of the Earth. There are no set rules for placing sources and receivers, and from an imaging perspective, the wider the distribution, the better the imaging. So in an ideal sense, having sources and receivers both on the surface and in the subsurface would be the optimal way to image the Earth. However, from a practical sense, in most cases, we have the sources and receivers on the surface of the Earth. So here we see two examples of seismic methods. On the left, surface to surface, and on the right, surface to borehole. As the waves propagate through the earth, there are many factors that impact the wave field, as shown in the figure on the left. So we start with something near the surface, and then due to the fact that the waves are propagating over some distance, you have a lot of things that impact that wave field. You have spherical divergence just by the distance from the source. You have the reflection off of the interfaces. You also have absorption, and then other complexities like peg leg multiples, scattering due to smaller features in the earth, and then instrument type of issues to deal with. So given the complexities of rock sequences as seen in outcrops and a vivid imagination of how this may impact a wave field, it sometimes makes you wonder how we can get a clear signal or image of the earth. However, these methods have proven to be effective for subsurface imaging all over the world in a wide variety of geologic environments. So what does the data look like for seismic? Well, on the left, we see examples of the surface to surface measurements. And what we're looking at here are referred to as shot profiles. And the position of the shot is on the left side of these profiles, where the energy that's arriving from the source is arriving at the earliest possible time. For surface to borehole measurements, data takes on a slightly different appearances due to the change in the geometry of our experiment. As the receiver gets deeper and deeper in the wellbore, the signal takes longer to arrive. As the receiver gets closer to subsurface reflections, such as this reflection, this event here, the arrival of these waves occurs sooner in time. And so this indicates that the wellbore is basically at the position of this subsurface reflection at this particular depth. So after processing, the end result is a 2D profile through the earth. Where the amplitudes are large, this indicates positions where there are changes in elastic properties. The coherence of these amplitudes relates to the continuity of the subsurface interfaces. The surface to borehole data, which is referred to as VSP, can also be processed into seismic traces, and these can be overlain on the surface seismic as a way to calibrate and understand what's going on in the earth. Because they're both seismic experiments, and in this case, they're both shear wave seismic experiments. The expectation is that what we see in the surface to borehole measurements should be very closely matched to the surface to surface measurements. And we can see from the correlation of these traces that this in fact is the case. The question becomes, how do we interpret these type of amplitude changes with depth? And how do these amplitudes relate to rock properties in the earth? So this schematic shows a representation of seismic inversion. So on the left, we see the geology of the earth as a series of rock packages with interfaces between the different rock types. The changes across these interfaces can be represented by these reflectivity spikes. The propagating seismic wave field is a wavelet. It interacts with the spikes to create the amplitudes we see in the seismic sections. Inversion is simply the processing of removing these wavelet effects and recovering the layered geologic model. So it's in fact taking the process in reverse. So inverting the shear wave seismic results in a profile of shear wave velocity. The arrival times of the waves in the wellbore VSP, in fact, there are two VSPs, can also be used to create a shear wave velocity log that directly corresponds with the inverted section. So we've got velocities in our cone penetrometer holes and velocities from the seismic. As this is a shallow seismic line across unconsolidated sediments, the rock property changes due to effective stress dominate the response and make actual lithology identification challenging. To minimize the changes due to effective stress, a simple normalization process is followed. After normalization, the silt and clay zones show a relatively constant set of properties, and the sand zones, which are indicative of the aquifers in the subsurface, stand out. So when the normalization is applied to the shear velocity profile, the picture of the subsurface comes into clear focus. The two aquifer zones, the upper and lower aquifer zones, stand out from the clay zones and show complexities that can now be related to subsurface stratigraphic variability. The next example is from the Fraser lowland near Vancouver, Canada, as shown in the index map. Yellow box shows a fuzzy outline of a near surface aquifer, which is hard to differentiate, but there's a big blob in the middle of this yellow outline. And the seismic has been acquired in various locations around and within the aquifer. All three shot profiles show a noise train in the middle, which is called ground roll. This is due to waves traveling along the surface of the Earth and not reflecting off of subsurface discontinuities. There's a fair bit of variability in the quality of the underlying seismic, which you can kind of see peeking out on the outside edges. And this is due to changes in the near surface of each of these three different seismic lines. The frequency spectra, which we see below the profiles, shows that on one line on the right, we have usable frequencies of up to 1,000 hertz, which is, that type of frequencies are basically unheard of in the oil industry. So as a part of the processing of seismic data, it's very important to remove the noise. So in this case, we know that we've got this low frequency ground roll, which does not represent changes in the subsurface. And the way to remove that is through a process called filtering. And when we look at the profiles before and after the application of a filter, we can now start to see the removal of the noise and coherent reflections that cut across the profiles from left to right, which is what we'd expect for our seismic profiles. So here is one of the final processed seismic profiles. So this is in fact an urban setting. So there's lots of farms and homes nearby the seismic lines. And one of the side benefits of that is that one of the key sources of subsurface information in this area are water well bores. These well bores only penetrate the upper 50 meters or so in this case. But the advantage is that they've been meticulously logged for changes in the different rocks and sediments. So this allows the reflections on the seismic to be correlated with a reasonable degree of confidence. And there's one zone in particular where you've got these interbedded reflections, and that nicely correlates with interbedded sands and shale in each of these, or sands and clay in each of these adjacent well bores. Here's another profile on the eastern edge of the aquifer. In this location, there are some reasonably deep well bores that have been drilled through a relatively uniform near-surface clay zone, which we can see with very little character on the seismic, and into the underlying aquifers. The bedrock, which is actually penetrated by one of these deeper wells, ties quite nicely with the higher amplitude continuous reflection in the middle of the profile. Okay, so back to the subject of inversion. We looked at one example, which is the shear wave inversion of a profile, and how that converts to a section of shear wave velocities. So there are many different inversion techniques, can basically be classified into 4 different categories. So we've got the bandpass elastic impedance inversion, the bandpass simultaneous inversion, the full bandwidth simultaneous inversion, and then a simultaneous geostatistical inversion. And one of the key differences, a simple bandpass elastic impedance inversion, we look at every trace within our seismic volume, what we're really looking at is a limited offset range of the seismic data and using that to, in our inversion, to characterize the Earth. For the other methodologies, the simultaneous inversions, we are taking the full range of seismic offsets that we saw in those rock profiles and using that to come up with our rock properties. So this gives us a lot of information to work with. The geostatistical inversion is of particular interest as it appears to have the potential to show the greatest amount of detail due to the broadening, which is the dashed block line, of the output frequency spectrum and the utilization of the full set of acquired seismic. So here is a simple model example to highlight the difference in the different inversion techniques. The band test technique nicely highlights the low impedance channel, but fails to show any details within it. So it becomes this kind of easy to see, almost uniform amplitude blob. Once we move into a full bandwidth inversion, we start to see variations across the channel, and you can argue you can interpret the top and base to a much better extent than the bandpass. However, due to the thickness of the channel compared to the wavelength of the seismic, we are not able to quantify any of the properties within the channel. So the real properties are shown on the right, and none of these properties are properly quantified due to the thickness. However, in the geostatistical inversion, we have the opportunity to match both the top, the thickness of the channel down to very small amounts, arguably less than 2 or 3 meters, as well as matching the properties within the channel. So this seems to be the most powerful of the inversion techniques. So just to add a bit more detail about geostatistical inversion, in many respects, it's quite similar to geologic modeling, with one notable exception. The measure data we want our models to honor also includes seismic, thus making it an inverse problem instead of just a simulation problem. In fact, this is the typical type of data you would expect to use as inputs. You've got a structural model containing horizons and faults, rock physics information, geostatistical relationship describing how properties vary in the different environment, seismic data, and a suite of well logs. Once this data is processed by the geostatistical inversion algorithm, a series of realizations of various rock and reservoir properties are produced. These can then be interpreted to gain insight into possibilities and uncertainties. So the final example shows the application of geostatistical inversion to a gas field in the northwest shelf of Australia. So in the cross plot, we've got well log data, and we see a clear separation of our different rock and fluid types. So our gas sands show the greatest separation from our brine sands and our shale. And so this large separation of elastic properties usually translates into large, very obvious seismic amplitudes. The ultimate aim of doing the inversion is to gain insights into reservoir property variations, such as the volume of shale. The VPVS is one of the possible inversion outputs, and this elastic property shows a very high correlation with our V shale property of interest. Here we see the final result. We've got the broadband seismic on the left, and very strong seismic amplitudes associated with the presence of gas in the reservoir. This section's in depth, so there's an expectation that, you know, any gas water contact is going to show up as a flat spot, and you can see this amplitude event at the base here, which represents the gas water contact. The problem with the seismic, it's not clear how thick and continuous the sands are. We know they're present by the large seismic amplitudes, but we don't have any way of distinguishing the thickness or even the continuity of these sands from well to well. We look at the inversion result on the other hand, so we've got the geostatistical inversion, and this clearly shows the reservoir rock variations that also correlate with our V shale logs in the wells. The end result is a product that shows where the reservoir is thickest and of high quality, and also shows the presence of possible barriers within the reservoir section, such as this shale in here, and the continuity of the sands seen in the wells. So we've got little model responses at the bottom here where we see the complex seismic response and a very simple depiction of the reservoir where the gas sands stand out very clearly from the background. So I've shown 3 different examples of seismic methods. Each method is different in terms of the frequencies observed and the type of propagating wave field, either shear wave or P wave. To understand the scale of the different examples, we have to think in terms of seismic wavelength, which is given by a simple expression of velocity divided by frequency. So we look at our 3 examples. We've got our shallow SH wave experiment, our shallow P wave, and then finally the broadband P wave oil industry example. And when we look at the shear wave seismic, that even though the dominant frequency is only 50 hertz, we can achieve the same resolution, so lambda over 4 is a typical measure of resolution, as the higher frequency P wave seismic. And the reason for this is due to the very low velocity of shear waves in those same sediments, 200 meters per second compared to the faster P waves at 1800 meters per second. For the broadband P wave, we've got a higher velocity and a lower frequency, and this gives us a much greater standard resolution of almost 19 meters for the broadband seismic. The key here is that, as we've talked about, if we go to a geostatistical inversion technology, that technology really explores the detection limit, which is better represented by this wavelength divided by 16. And we can even see that brought out in our example because there are two events at the very top, which are tied by the wells, where we've got a 5-meter gas reservoir and a 7-meter gas reservoir, which are shown quite clearly in the inversion result. So that's where a detection limit type of feature becomes possible when we're dealing with the right style of inversion technology. So in conclusion, seismic methods have been shown to be useful for both near surface investigation as well as deep exploration objectives. Seismic methods are sensitive to changes in subsurface elastic properties, P velocity, shear velocity, and density. The scale of measurement is linked to the wavelength of the propagating seismic wave field. And seismic inversion provides a way to transform seismic amplitudes into meaningful rock properties. Thank you.
Thank you, Kevin. It was a great presentation detailing about the seismic methods and how that to be interpreted and to be acquired. Now it's the time to go for some of the question and answers time. So please, if you have a question and you want to ask, unmute the microphone and ask the question, or type into the chat boxes so that we can read to him. So if there is no questions yet, I would like to ask you about the resolution of the seismic interpretation versus the stratigraphy. Like when you look on your seismic horizon, how thick it's going to be your stratigraphic correlation, how that can be, like with in meters or less than meters, how that can be correlated?
Well, I guess the example I showed for, typical oil industry seismic, you could interpret reservoirs down to a very fine level of detail. Now, when it comes to sort of general stratigraphy, I mean, the advantage of a reservoir sand is it's full of gas and it shows a very large contrast with the surrounding rocks. And so in that situation, you have the ability to see something at a fairly small scale. However, when it comes to stratigraphic variations that may not have gas presence, well, then it changes and it becomes, something thicker than that, that 5-meter cutoff. So in some of those cases, you're looking at something that might be no thicker than, or no finer than 10 meters in scale. And it's that averaging which you kind of have to consider from a stratigraphic point of view. So you don't see the fine scale features that you see in outcrop, which are certainly in centimeters or meter in scale. And you have to average those stratigraphic variations to imagine what the seismic is actually showing.
No, that's good answer. I think one of the two questions are there. The first question from Alex Anthony Maliakal: for better interpretation, which software can be used commonly?
By interpretation, you mean inversion?
That's right,
Yes.
maybe.
Yeah, so if inversion is the objective, which in my mind is always a useful exercise to improve interpretation, then I mean, certainly my preference for inversion is the CGG JSON software, which was used to do that geostatistical inversion work off the Northwest Shelf.
with regards to that question, like, I mean, if students want, any university wants, do you know CGG will be providing some of the university license or any that kind?
I think they do provide it to quite a few different universities. And I guess it's just a question of making a proposal and submitting it, because they're quite open to, I mean, I know the universities in Perth both have copies of the CGG JSON software, as well as the other, another popular inversion software is Hampson Russell, which is also by CGG. And other vendors like Icon and I believe they also provide universities with free copies of the software. So, from an educational perspective, everyone should have access to this kind of technology. And it's really just a question of making a proposal to CGG and getting access.
That's a very handy answer. So yeah, anyone interested into looking into any kind of seismic inversion interpretation or any that kind, yeah, you can access to CGG for a good proposal. So there is another question from Devi Prasanna. How seismostratigraphic interpretation helps to find out different depositional environment?
Well, I guess that's almost a talk in itself, is seismic geomorphology and really it comes partly from experience, as well as partly from understanding your basins and partly from the different shapes that you see as you slice through your seismic volumes, because in the channelized environment of the Triassic, when you slice through those environments, the channels are very obvious. They create, very obvious channel-like features. And as you approach the paleo shorelines, you start to see the disappearance of those channels. You see, deltaic type features, and so you start to interpret your data that way. But really, it's an integrated approach. You have to understand the environment you're interpreting, and then look through amplitude slices, either through inversion volumes or the seismic itself, and look for the features that you would expect in those different environments.
Thank you very much for that. Is there any other questions? Otherwise, I would like to ask one more question. During the advancement of the big data analytics or the data machine learning or artificial intelligence, how far they both are integrating each other, or how that can be useful for interpretations or looking into details on the reservoir quality or reservoir properties, how that's related?
Well, I think there is some work going on in that space where, people have suggested that the actual process of seismic inversion can be dealt with as a, machine learning or big data type of experiment. And perhaps that's the case, although in the case of inversion, you're usually dealing with known physics and a fairly solvable problem with a reasonable degree of uncertainty. So in a sense, you're kind of wasting the machine time by solving the inversion. However, if you focus on the output of the inversion and try to make correlations with whatever you're looking for, rock properties, reservoir quality, etc., then I think it's been demonstrated that you can achieve some very high quality results looking at the spatial distribution of those properties.
That's a good point. To get a detailed reservoir quality or rock properties from the seismic, to relate with um, backward thinking like a stratigraphy, sequence stratigraphy, and to the petrophysical attributes to understand a bit better way, or like a upscaling towards micro, or to narrow down to centimeter to meter sort of resolution from the reservoir quality or rock properties. Yeah, that's great.
Yeah. I mean, the reality is that seismic is one of the few methods we have that gives us this incredible spatial detail. And we know that our well logs are much finer scale, our well logs in our core, than the seismic, but that is vertical detail, not spatial detail. And, you know, I think we're kidding ourselves if we think we can populate models simply by interpolating our wells. You know, we really have to leverage that spatial detail in the seismic to fill in the gaps between the wells. And it's not going to be a perfect solution because there is this big difference in scale, but it really gives us the best opportunity to honor all of our data, both the well data and the seismic simultaneously.
Yeah, that's right. Yeah, thank you for that. Is there any other questions coming up? Seems to be a few of them putting some of the comments like nice presentation, nice, giving valuable information, very nice presentation. Yeah.
I can't see the comments on my end.
Yeah, you can look at that as well. Yeah, yeah.
Sharing again.
So, is there any questions regarding the seismic? If there is no more questions, like, thank you very much, Kevin. Thank you very much for accepting the invitation and giving a very good talk to especially to the student level, to the professionals, and that's so informative. So, Lindo, do you want to say a few words?
Yeah, Kevin, thank you very much. It was very nice. Though normally at university level, we do not get such talk, especially about different geophysical methods that is used in petroleum area. So that was really a good opportunity. I'm sure that students must have really enjoyed it. So thank you so much. It's sad that we don't get much questions from the students part, but probably you could also add, like if they have to concentrate more to the industry, what aspect they should focus on in their study or in during their curriculum. Probably you can give some light into that, because most of the participants are students. Probably they would benefit from that.
Yeah, I guess in my experience, to do geophysics hands-on, you know, really is the most valuable. And, you know, so, you know, there's not a lot of opportunities as an undergraduate to do these experiments. Ideally, you'll have access to some equipment, and it really doesn't take very much, you know, really basic seismic equipment with, you know, I mean, the examples I showed was some fairly old technology, you know, 24 channels and you know, a bunch of geophones and cables all hooked up. And ideally, the university will have that sort of equipment that gives the students a chance to, you know, do their own experiments. And I think when you get a chance to acquire your own data, you know, generate the waves yourself, record the data, process it into a section of the earth, that sort of insight is invaluable. And ideally, every university that teaches geophysics should have access to that type of equipment. So I don't know what the situation is in India, and it's, you know, I think I had in both my undergraduate and graduate schools the access to that type of equipment to really understand, you know, some of the complications, some of the limitations. You know, you can't acquire shear data in every environment. You can't, you know, you have to work with in some areas which have cars and trucks and other sources of noise, but you still have to to try and acquire some seismic data. And those kind of insights are best to obtain by doing the work yourself.
Yeah, thank you. That's nice.
Yeah,
Dr.
thank
Saji?
you. Yeah, we will. I mean, there is a 4 minutes to go for the next session time, but I think we will start introducing the next speaker. Then the time will be comes up. So I'm going to introduce the next speaker. This is a session for development in stratigraphy and sedimentology. So our third presentation, we have Dr. Mahmoud Al-Nasga. He is from Saudi Arabia. He will be presenting on the subject, sequence stratigraphy of the upper Pennsylvanian Canyon and Cisco formations in Sarcoke Field, West Texas. Insight into the late Paleozoic glaciation. Dr. Mahmoud has more than 10 years experience in carbonate sedimentology and stratigraphy and reservoir characterization. So we are going to listen a presentation from some of the carbonate sedimentology. So at the moment, Mahmoud focused in Arabian plate stratigraphy from Carbonaceous through Cretaceous and the global events recorded through its evolution. He holds a BSc from Durham University in UK and an MSc and PhD from University of Texas at Austin. So by that, I would like to welcome Dr. Mahmoud for the talk.
Thank you, Saju, for the invitation. Let me get set up here with my presentation. Let me see. Okay. I apologize for this.
Did you find?
Yeah.
Okay, that's good. Coming.
Do you see my screen now?
Yeah, it's coming.
All right. Hello, everyone. Today I'm going to talk about the sequence stratigraphy and geomodeling of the Upper Pennsylvanian Canyon and Cisco formations in Sarcoke Field in West Texas, with some insights into the late Paleozoic glaciation. So the research motivation for this is that there are major questions were raised about the character of the late Pennsylvania. The late Pennsylvania is kind of the U.S. late Carboniferous state, right? About the late Pennsylvanian ice. So the long-held model proposed.
May I interrupt? I'm sorry to interrupt. You are not audible clearly. It's your voice is vibrating in between. So do you have any chance to make it stable a little bit?
Let me try and.
If you have a headset, that would do, I guess.
If you're closer, that's the time you are on the right side. It's much clear, or your left side, it's much clear. If you move the face on the other side, it's going wave.
Okay.
I think
let me try and stop the video. Can you hear me?
Yep.
I don't know if it's better or worse.
No, the other one with the video, it's also fine. The head movement is making a bit of a low voice.
Okay.
How about now? Is the voice okay now?
Yep.
Okay.
What about Lindo?
Yeah, it's all right. If you have the headset, that would help, I guess, because when you move here and there, then that's only the disturbance comes. Otherwise, it's okay. Yeah.
Unfortunately, I don't have a headset.
It's all right, no problem. I think you should, I mean, you can continue now. It's okay.
Okay.
Please try it, yeah.
So major questions were raised about the character of the late Pennsylvanian ice house. And the long-held model is that the peak of late Paleozoic ice house was during the late Pennsylvanian earliest Permian. However, the ice sheet intensity were questioned recently by Isabel Montanez, Chris Fieldings, and others based on data from Australia, as well as from the Araucanian and Spring Break formations in Nevada and California. So the challenge that they came up with goes along against well-developed analyses from Sacramento Mountain and other data sets around the globe that strongly suggest that the greatest amplitude of eustatic fluctuation was actually in the Virgilian stage. So the research question that we have is, what was the stratigraphic record from low paleo latitudes as far-field methods to reveal about the history of glaciation during the late Pennsylvanian? And what was the nature of the minimum eustatic amplitude that can be inferred from these records? I will touch briefly, because this is, I'll try to touch briefly on the best geological practices for modeling such ice house carbonate reservoirs. So some background. So prior to 2004, most of the studies from sedimentology, diagenesis, and geochemistry have shown that the Missouri and Virgilian stages were a time of ice house conditions. Now, recent studies have suggested that these stages reflect interglacial or even ice-free conditions. So which one is it? So this is kind of the background and the motivation of this research. So this is a summary of studies and the methods that were used to kind of estimate the glacial-eustatic amplitude in the late Carboniferous. So sedimentology has been used to estimate these glaciation 1D and 2D. When we say 1D and 2D, basically 1D is built, and we'll talk about it, it's built on 1D measured sections. The 2D is when you establish kind of 3D, 2D stratigraphic framework, and the 3D is kind of when you use 3D seismic, which we used in our study. Diagenesis was used as well to estimate the eustatic fall of sea level when, by Goldstein, for example, in the Holder Formation, as well as the geochemistry. Geochemistry usually, mostly use delta 18O to estimate the eustatic fluctuation. There is also the paleo valleys, like studies of Fieldman, 2005. And the last method is kind of the geological modeling, where ice was used, as well as Mr. Sediment by Goldhammer in 1994. The color codes here reflect the glacial-static amplitude that they estimated. So all the blues estimate that this late Carboniferous is actually an ice house with more than 40 meters of eustatic fluctuations, where the greens are estimated that this period was a greenhouse where we don't have actually ice in there. So some background here, Weavers and Powell in 1987, they studied transgressive, regressive depositional sequences in Euro-America, and they had defined 4 regressive sequences. You can see them numbered on the right, and 1 transgressive regressive sequence. Now, the latest Pennsylvanian, they described it as having high amplitude, high frequency eustatic fluctuation, which had a period of 400 kiloyear, which is similar to the eccentricity of Milankovitch forcing. Their work actually covered a deeper section in time, all the way to the Devonian. And this map here shows the early Devonian, but what I want to take from this is the location of the data set that they use. So they have data from these numbers are these numbers right here. So they have data from South America, Africa, Arabia. They have from Antarctica, from India, as well as Australia. And you can see here that most of these areas, they have glaciogenic, which is the diagonal pattern here. They have glaciogenic deposits, which are related to glaciers, that is. So when we looked at Haeckel in 1994, where he looked at the Devonian to Virgilian succession from the mid-continent in the US, he looked at the section from Iowa all the way to southern Kansas, and he characterized, or his results shows that the Lake Pennsylvania actually characterized by high frequency, high amplitude static fluctuation. What you can see here, this is the shore, which is almost at sea level, you know, and this is the black shade right here, which is the basin. And you can see that it's fluctuating all the way here. So it suggests that you have really high frequency, high amplitude static fluctuation during that time. This is an example from 1D and 2D sequence stratigraphic analysis. In this study, Sorigan and Giles in 1999, when they worked on the Panther Sea Formation in the Lake Pennsylvania, the Sacramento Mountain, they estimated from the preserved relief of the phylloid mounds that the eustatic fluctuation were at least 80 meters. So the reds here are exposure features, and the blues are phylloid mounds, which kind of like a modern reef, but more of like a Halimeda in the Bahamas, for example. Another 2D method is the estimating eustatic fall from incised valley or paleo valleys. This study is by Feldman in 2005, where they also studied the mid-continent clinotherms going from Iowa all the way to Kansas. And you can see that some of the paleo valleys, they are actually cutting down even in the underlying sequence. So there is at least a 30 meter of eustatic sea level fall, and they can reach as much as 120. So Fielding, in 2008, when he studied Eastern Australia, he came up with 4 Carboniferous glacial events and 4 Permian glacial events. And in the Lake Pennsylvania, he thought that this area was an interglacial or ice-free period. And this is where all this kind of debate started. And it actually was based on their work in 2004, okay, when they worked on the JoJo route in the Galilee Basin. And they defined these glacial events. So this is Carboniferous 4 and this is Permian 1. They defined these glacial events based on the presence or absence of dynamic tide. And as scientists, we all know that absence of evidence is not evidence of absence, right? Then in 2010, Bishop, when he was doing his PhD at UC Davis, he studied the Arrow Canyon in Nevada. And they concluded that the Lake Pennsylvania was a time of greenhouse or ice-free period. What you see here on the left is the depositional facies. So they kind of inferred the water depth for all these depositional facies. And on the right is their interpretation of the range of the eustatic change. So this is from 0 to 20 to 80. So here in the Moscovian or Devonian, they show that you have huge static fluctuation. The range is huge. While in the late Pennsylvanian, they have suggested that you are fluctuating at least, at most 20 meters. This research was followed in 2012 by the work of Martin in 2012 when she was doing her master again at UC Davis, and she studied the bird spring platform. And their conclusion is that the late Virgilian again and the Mesorean were actually times of ice-free periods. When we look at the synthesis of Isabel work in 2003, we can see that a lot of these areas in Africa, in India, in Australia, South America, and Africa, they had glacial deposits, terrestrial, the yellows, and the lacustrine, and the marine, in purple. And Fielding, here is in the green, he suggested that this period was an interglacial or ice-free period. I would argue that actually when you have diamectites, is the interglacial periods, is when you melt the ice and you start moving the sediments, rather than the contrary. So what did we do to kind of answer this question? So we started with high resolution sequence stratigraphy. We used that to kind of refine the late Pennsylvanian eustatic curve. And we used all this information to build a 3D reservoir model using different modeling techniques. So this is kind of the outline of the data set. We'll go through icehouse climate and its influence on the rec record. We'll look into the regional setting of the sac rock field. We'll go through the depositional phases and the stratigraphic framework. I'll show you how we constructed the static sea level curve. And I will touch briefly on the 3D reservoir model. So when we talk about climate, there are three major settings. There's icehouse, there is transitional, and there is greenhouse. And before we dive into this, when we talk about icehouse, what's an icehouse? It's not an igloo, but it's a climate. An icehouse is a climate that's defined as periods in the geological record that have major polar ice caps that have marine icebergs. And by major polar ice caps, we mean that you have presence of ice sheets that extend for at least 5,000 square kilometer and are at least 1 mile thick. Okay. When comparing different climatic settings, there are several distinguishing factors between them. For example, when we look at the major ice caps, they're really big, they're dominant during icehouse. When we look at the transitional, they become smaller, and they're almost non-existent in greenhouse. Another thing is when we look at the polar to equator thermal gradient, you will have a steep thermal gradient between the polar areas and the equator during icehouse, while you have much gentler slope during greenhouse. Another thing is when you look at the oxic conditions during icehouse conditions, the oceans would be more oxygenated compared to greenhouse. And that's because the simple fact that when temperature drops, gases are easily dissolved into the oceans. But during greenhouse conditions, it's very difficult to dissolve oxygen into the oceans. And there is a list of things that are associated with this. So the climatic conditions are very important on whatever you work on. You have to understand that. Now, why is it important? We'll go through this now. So through the Earth history, okay, periods have been separated into ice house, greenhouse, ice house, greenhouse. And that's very important. Why? Because during ice house, you will be dominated by aragonite and high mag calcites, which is metastable to unstable minerals, compared to greenhouse settings where you have low mag calcite, which is more stable. So you are more prone to diagenesis. We'll look at some of the diagenetic effects here in a moment, but it's very important to know where you are in the geological record. Now, under each climatic setting, there exists a range of predictable stratigraphic characters, including cycle stacking patterns, platform architecture, development of sequence boundaries, and diagenetic patterns. The premise is that during ice house conditions, when ice caps form and melt, there exists a strong eustatic fluctuations at the 20 to 400 kiloyear frequency. This greater eustatic amplitude drives a complex stratigraphic architecture on the platform with multiple unconformities, internal on-lab, and frequent exposure surfaces. In contrast, when we look at the greenhouse settings, they are characterized by minimal eustatic fluctuation, actually generally less than 10 meters, which gives rise to simpler regional stratigraphic architecture. Carbonate factory becomes very efficient. So you're filling most of the accommodation space, and you actually exceed the creation of accommodation space, that you end up having large platforms with highly correlative shelf-top ratios. In transitional times between ice house and greenhouse, this sits somewhere between the oversimplified greenhouse world and the non-equilibrium architecture of ice house systems. So this is my study area right here in West Texas. This is the paleo equator during the middle Pennsylvania. That's where it was situated. And this is a paleogeographic map of the black here is the greater Permian Basin, and these are the abbreviated letters are the structural components of the Permian Basin, and the MB here is the Midland Basin, where the Horseshoe Atoll, that's the horseshoe, looks like a horseshoe. And this is where my data set is coming from. So the Horseshoe Atoll was subsiding much faster than the surrounding areas. So the CBB, this is the Central Basin Platform, which is this one right here. And the Midland Basin was subsiding so much higher than CBB, which allows for a more complete stratigraphic record, which is important in what we're trying to do. So if we look at thickness map, this is where the sack rock is. Stratigraphically, the section has been dated using fuselinite, and it is Mesorian to Virgilian. These are previous studies of reservoir characterization, where they divided the reservoir based on fuselinites. This is our study. We kind of included the upper or the early Cisco into our canyon, and we came up with 5 sequences for the Cisco. So my data set has 11 cores with a total footage of 7,000 feet and covering an interval from the Strome, which is Devonian in age, through the early Wolfcampian, which is Assyrian or early Permian in age. We have more than 560 logs with the gamma ray neutron. Some of the wells will have a full suite of logs. And the biostratigraphic picks for all the cored wells come from Schatzinger work when he did his PhD in 1987. And we have a 3D seismic volume as well. So This is on the left here, you see a map of the top Cisco formation. And the black dots here are the wells with core intervals. And on the right, it shows you the core interval that is covered by intervals. So the workflow that we follow is that we do the detailed sedimentology, including the core description, topographic analysis. We use that to build our 1D stacking analysis and the 2D high resolution framework. We use all this to feed into our paleoclimate interpretation, from estimating water depth for the positional facies and refining the static curve. And we use everything in here to feed into our 3D reservoir model using different modeling techniques. So this is one of the sheets, one of the description sheets that we use. I'll just zoom in here to show you what kind of data that we capture. So you see all these tracks in here. There is stylolite and fracture that are recorded, the pore types, the mineralogical composition, whether it's dolomite, limestone, evaporite, sandstone, you name it. The sedimentary structures, cross-bedding, lamination, surfaces, bioturbation. And then we have modified Dunham kind of texture. So we have the mudstone, the waxstone, the backstone, and grainstone, which is modified later on by Clover and Embry in 1971, where you have the clotestone and the rodstone. And this is a track for cycle analysis, where you have exposure and you expect to have cycle top in here. You pick one here. We have a track for grainstone, for grain size. And we have a track for the type of fossils and their abundance. So we record whether it's rare, common, and abundant. So based on this, we identified 5 facies association: basin, slope, mound, middle shelf, and shore. We kind of use this to build our positional model, and the process is kind of iterative. The more core we have, the more control that we have, and the more that we go back and refine our model. So basin facies association consists of this black silicic-plastic mudstone. It's generally poorly preserved, but it's there. And this is how we link our core to the logs, and you can see it clearly on the log because it has hot gamma ray signature, and you can tell that because of the crossover of the density and Newton. Then we have the slope facies association. We have 3 types of facies here. We have skeletal grainstones, and basically these are these grainstones, and you can see the steep angle of the position of these because you are on a slope. Then we have the crinoid rodstone, floatstone. These are interpreted as slope turbidites, where you can see upward fining in this interval. You still see the inclination of the beds. And then you have the lithoclastic breccia, which are kind of like slope failure deposits or debris flow deposits. You can see the big clast in here, the big clast in here. They're subangular to subangular clast. So then we have the mound facies association. The mound basically is this pink facies, which is like a reef or Alameda bank of today, if anybody has seen it. So we have the phylloid alder bandstone, which is the mound core, and then we have crinoid phylloid waxstone backstone, which is the kind of the flank facies. You look on the right here, these potato chip-like things, these are the phylloids. They're generally replaced because they're aragonite. So the aragonite is very metastable and gets dissolved and gets replaced by low-mac calcite, as you can see here. This is the outline of a phylloid plate, and you can see it's replaced by low-mac calcite. This is the crinoid phyloid limestone. This is the slag facies. Basically, these are the phyloids in here. You can see them, and these are the crinoids. These are just sea orchids, right? Sometimes you don't get a full replacement, and you see these holes. These were phyloid algae that was dissolved and was never replaced. So they make a good reservoir fishes. Then we have the middle shell facies association. These are generally composed of fuselinids and crinoids. These are the fuselinids, which are big benthic forams. These are these things here. And they sometimes are bioturbated. And this is the grainstone right here. We don't see any mud in the matrix. It's all cemented. These are the fuselinids. These are the crinoids. So these are the crinoids right here. And these are little circular things are the fuselinids. Then we have the shoal facies association, where we have oid grainstone with subaerial exposure features, which will be seen, and the phyloid skeletal grainstone. So this is on the right here is a core photo of these. I don't know if you can see them. We make them out. These are the ooids. You can see them here. Their textbook. But you can see that their core is dissolved, and that's because of their aragonetic nature. Sometimes they become completely calitrified. That's basically when sea level drops and you have a lot of flush of meteoric waters, and they become completely dissolved, and you end up with this kind of moldy network of the grains. You can see some of the grains preserved, and you can see the concentric lamina in here. So you know that this was actually an oil. And this is the phyloid skeletal grainstone. This is you can see the lamination in this facies, but it's mostly composed of phyloids, fuselinids, forams, and crinoids. These are some of the exposure features right here. You don't see these commonly. I mean, this is a great opportunity to look at these. These are some rootlets right here. All these is digenetic. These are not bioturbation. They look like bioturbation, but when you look at under the microscope, they're ooids. You can see meniscus cements and all other features for exposure. So once I finished describing all the wells, I started picking shallowing upward cycles. So kind of do the 1D analysis. You can see that I'm shallowing from this species to this species. I'm shallowing from this species to this species. So I'm doing this for all my wells, and these are my interpretation. And I try to extrapolate these into uncored wells to build the framework. Well lines are very important. As Mohammed said, you only have, if you're lucky, you'll have 10% of core in your field. It's usually less than that in most of the fields that you work on. And so you will rely heavily on the wireline logs. And this is one of the cycles that is a bit based on the wireline. So we do this 1D analysis for all the 11 wells, and these are a kind of a snapshot of the examples that we see. You can see that we're picking these shallowing upward cycles with their wireline signature. This is a flood, shallowing up, flood, shallowing up, flood, shallowing up, shallowing up. And you can see both the wireline log behavior as well as the rocks. You can see the deeper facies and the shallower facies, deeper facies and the shallower facies. Same scenario here. See the deeper facies and the shallower facies. You can see the same trend. So wireline logs are very powerful. So we use this to extrapolate our correlation or our surfaces from core to uncore log. When you look at the canyon, you can see it's pretty straightforward, very layer cake, simple to correlate. When you look at the Cisco, you see features that you cannot correlate most of the time because of the nature of the rocks and the nature of the historic fluctuations. So in the canyon, which is abbreviated here as CAN, and the Cisco, which is abbreviated CI in here, we have defined 4 high-frequency sequences. These are generally very correlative, as you saw from the previous cross-section. You see here, they are very correlative. Easy to correlate. You can see the same signature, boom, boom, boom. And then you have the Cisco, which is very difficult to correlate. And we have 5 sequences in here. When we look at the seismic, this is the top of the canyon, this is the top of the Cisco. You can see that the Cisco is continuous in here, and it's reflected in the kind of layer cake geometry. In the Cisco, it's more shingle, and it's related to the static fluctuation that we're going to talk about in a few minutes. Before I dive into how we constructed the static field curve, I have to talk about a very important concept. It's called missed beats of deposition. Missed beats are stratigraphic records that are not considered due to their absence in your study area. So you have a study area, as soon as you step out of it, and you don't have control, that data will be missed, right? So missed beats can be produced by either if you the deposition beyond the platform where you're working, or pulse transgression, or drop in sea level, subaerial exposure in your study area, which I will explain right now in a cartoon to make it much easier. So if this is the area in black box of your investigation, and this is time 0, so you have the inner shelf, the middle shelf, and the outer shelf deposits. Right? Sea level starts to drop, and you start depositing facies off the platform right here, and then a platform here, and a platform here, and then sea level starts to rise again, and you start depositing on the platform. If you place a well here, or you measure a section here, you will see only this section. And if you're lucky and you have a well here, you will say, okay, I have a transgression where my facies started to backstep. But you will have no idea that sea level actually dropped to here, because it falls beyond your control. Another example is when you have pulse transgression or pulse rise in sea level. So if this is time 0, you start depositing these. Sea level starts to rise. You bring in the facies all the way on the top of the platform right here. And then sea level starts to rise again. The assumption is that this is one event. And you will assume, because we use the facies as sea level indicator, we will have no recollection that actually the sea level has risen beyond the first time it rose. And when we did our high resolution sequence stratigraphy, you please mind the scale here. The field here is very small. This is about 15 kilometers. So it's very small. We found this much of missed beats. If I only have this well, I will have no idea that sea level have dropped all the way here. And the same story can be said here. If I only had this well, I would have no idea what happened here. So when we construct eustatic sea level curve, is basically we're using published work and modern analogs to infer the best estimates of water depth for the deposition of the key facies. For example, when you look at the oil grindstone, there are examples in Abu Dhabi, in UAE, we look at the Bahamas, we look at the Turks and Caicos, and we see that they range in the position from 0, which refers to sea level, up to 5 meters below sea level. When we look at the Halimeda as analog for the phylloid, for example, in the Great Barrier Reefs, which I will show you an example in a few minutes now, it can range from 20 to 150 meters. And in our study, we use the minimum sea level drop. So we don't want to overestimate the static change. So if we look at the Turks and Caicos right here as an example, these are all old shoals, if anybody has ever been there. And you can see these are oils. They're all made of oils. If we look at the Alameda, this is a study by Orme and Salman, where they used a GPR, ground penetrating radar, to map the Great Barrier Reef. You can see that these Alamedas, okay, this is the depth here in meters, they exist beyond 25 meters. Okay, these are the reefs, these are the corals. So for the Alameda, for example, we used 20 meters. And we came up with these water depth for each of the phases. So for the oil greenstone, it ranges from 0 to 5. For the phylloid boundary stone, it ranges from 20 to 150. But for our purposes, to estimate the minimum eustatic fluctuation, we use 20 meters. So we always use the minimum number. And basically, we construct a eustatic sea level chord for each one of the wells. So this is the well right here. These are the positional phase sheets. These are our 1D static analyses. Okay, and these are the depths, right? So these are 0. This is storm with base, and this is the basin, which is like 35 meters. So when we see shale, we put a point here. When we go all the way to the ooids with exposure, we see how much the exposure is penetrating the cycle tau, and we kind of draw it here. And we do it all the way through the well, and then we kind of come up with this. Now, because of the problem of missed beats, right? So we have areas. This is another cross section. For example, in 11-15, okay, records more section than 17.5, 17-5, because it's on the crest, sea level drops all the way here. You don't have any record of this, but you actually, when you have more control points, you start to record this of the platform. Again, in sequence number 34, right here, was only recorded in this well, which is structurally lower than the rest. And the same can be said about 35. And then they all start to record the same trend. So if you have if you don't have access to this data, all this data will be missed, and you will assume that this actually did not fluctuate much. So our conclusion is that the Lake Pennsylvania, okay, the Julian and Missouri are characterized by high frequency, high amplitude eustatic fluctuation, where you have at least 40 meters of eustatic fluctuations. And contrary to Fielding and contrary to Bishop, we feel that during the Lake Pennsylvania there has been a significant glaciation during that period. When we do a synthesis with other data sets, when we look at the atmospheric CO2, okay, and this is from Montaney's work corrected from 2007, and we look at the delta 18O for the same interval from the Nacken Basin for the work of Chen in 2012, 2016. We see that there is an excursion of at least 2.1 per mil, which is higher than the last glacial maximum, which was 1.8, where we had 120 meters of sea level drop. Of course, the atmospheric CO2, what you see here, is most likely it's lagging from what we understand from the climate model. CO2, atmospheric CO2 always lags behind direct measurements. And it's because you take time as the climate cools, then you dissolve more CO2 into the oceans, and then you have a positive feedback loop. So it's always lagging. And when we dive deeper into Australia to kind of assess fielding work, okay, these are Diaz sections from 1983, where he did a cross section across the entire Australian plate. The section starts from Devonian sediments. This is the Devonian, and this is the Ordovician basement, and all the section is the Carboniferous. So this is the Jojo Grove, and this is the Galilee Basin where fielding work. And this is, if you remember, this is C4 of fielding work. And this section is what he attributed to lack any glacial deposits, which is true. According to Diaz, we don't have any glacial deposits in here. But if you look laterally equivalent to it, the same age rock units, you have glaciers. And this can be explained easily by ice model that was put by Isabel in 2003, which they did 3-stage models. So if sea level dropped 50 meters, then the extent of ice sheet in Gondwana will reach the southern part of Antarctica. If sea level drops 100 meters, this is how much ice you need to grow in Gondwana, which almost made it to Eastern Australia. And if you have 200 meters of water drop, or sea level drop, then maybe the glaciers will have reached the Galilee Basin. So maybe it didn't reach there, and kind of this is arguably why you don't see any of the glacial deposits on Eastern Australia in the Galilee Basin. So kind of in synthesis, we have established kind of a conceptual model for the SACRA. We constructed the high resolution sequence stratigraphic framework. We used the stratigraphic framework to construct a refined historic curve. And we concluded that the Lake Pennsylvania was a time of significant glaciation with high frequency, high amplitude historic fluctuations. I'll try to be brief on the geomodeling part of this, but I want to show you the importance of what we did. So we kind of used all this as input, the seismic, the white line logs, the conceptual model for our model. So we used that, we started with structural modeling, basically generating surfaces and whatnot. We built a 9 million cells model. Then for facies modeling, we upscaled the wells, we did the baryogram analysis, and then we used the SIS, which is sequential indicator simulation, or truncated, we tested truncated Gaussian simulation, and the multi-point statistics. And then we did the physical model. So first thing, we calibrated all our logs to the logs, okay, all our code to the logs. Then we extrapolated the picks from core to uncored wells. Then we used the seismic to interpret our horizons, and then we came up with a velocity model to kind of link the seismic to the log and kind of convert the time into depth. And we came up with our converted horizons. We came up with the zones and the layering. And this is just to show you the density of the data. This is how much wells I have in this very confined reservoir in the US. So the modeling techniques that we use is actually 3 types: sequential indicator simulation, the truncated Gaussian simulation, and multi-point statistics. Okay. I don't know. Sequential indicator simulation, okay, handles each phase sheet, each depositional phase sheet, okay, as a separate entity when spatial position is not actually is constrained. The truncated Gaussian simulation, okay, is based on order species proportion and their spatial distribution. So if you have a delta, for example, you have the delta front, and in front of it you have the pro delta and then the base. So if you start to model it and it sees only the delta front, it will always put it against pro delta, will not bring the base input. But the problem is, when you are in an ice house where sea level fluctuation is high, you might actually have delta front, and on top of it, you have basin deposits. So, and all the models were later confined by training images. I'm not going to get into the details, I'll just go to the results. So this is the SIS, or sequential indicator simulation. I'm not a very big fan of it because you can see that I don't have any basinal deposits, because in the core, they don't core the basinal stuff. So proportionally in the core, you don't have much of that facies represented in your control data. And when it starts to simulate, it will give it a smaller proportion. So the model becomes off. And when we use the training image, it gave better results, but it was very rigid, especially on the edges here. We tried to change the property from discrete to continuous. It became better, but it will not be my choice of model. When we use the truncated Gaussian simulation, okay, again, it gave very wrong, geologically unsound results, right? So the black are the basinal stuff, and the red here, you can see the limit of the platform, and I have basinal stuff and slope deposits on the platform, which is incorrect. And I have platform facies in the basinal stuff. Again, it has an order tract of facies, but it does not have a geological sense. When we constrain it by training image and facies proportion function, it became better, but it's very rigid. You can see that it's not really geologically sound. We tried to change again the property from discrete to continuous, and it gave better results, but it's too rigid. I don't think it will be my choice for model. The best model came out of the multi-point statistics, in my opinion, because it actually requires a training image as an input from the beginning. These results at the edges here were a bit rigid because of the property was discrete, but we fixed it later on. But I don't have a dumb image for it. It became much better. And then we did the petrophysical models for the facies, for the Cisco and the canyon. And you can see that it has really good agreement with the rock properties. This is the same one here, right? And this is the permeability. I will not go much into the details. So in summary, we kind of built a late Pennsylvanian period, and it was actually characterized by significant glaciation, and we refined the sea level curve. And I showed you how important it is to understand the limit of your data when you draw conclusions. It can drive you to draw actually wrong conclusions. With this, I'd like to acknowledge all my colleagues at the University of Texas, and the Bureau of Economy of Geology, and the Reservoir Characterization Research Lab. And if there are any questions, I would be more than happy to answer.
Hello, Mahsood. Hello, am I audible? Yeah, thank you very much. That was indeed a great talk, though we had little difficulty in hearing in between, but it went very well. I think if any of the participants have any question, one questions may be entertained now because we are already running short of time. If any quick question, you may ask now. Participants, please take this time. I do not see any questions in the chat box as well. So if you have,
if there is no question, I would like to ask another question to Mahmoud.
Yes,
yeah,
please.
please.
In your facies association, have you looked at any compaction rate, each of these facies, and do you see any changes on the compaction?
The compaction and decompaction, when we did the subsidence, when we calculated the subsidence, when actually we did a decompaction rate, and it was not done by me, it was done by a friend of mine, Dr. Yasser Zair, and we do see a change in decompaction, especially in the shade. It was calculated up to 70% in some areas. And the grainstone was the most resistant rock, but usually it has a finite strength. And when we try to calculate the Young's modulus, it usually crumbles because of the diagenesis. But
Yep.
there is we did decompaction, and we used a package software. What it was called? Elfin. It was Elfin software.
Okay.
Yeah, thank you very much.
Thank you very much for that.
Thank you once again, Mahmoud Hassan Al Nas. It was really a great talk, and thank you so much. Since we are running short of time, I think we should go ahead with the next talk. So next, let me introduce the next speaker of the day. I would like to introduce Dr. Saju Manacheri, who was the chair of the previous session, to give a talk on significance of sedimentology inside characterization for geological storage of carbon dioxide. Dr. Saju Manacheri is a sedimentologist and a reservoir quality geologist from Perth-based consultancy in Australia. He has got more than 18 years of international experience in oil and gas industry with an integrated approach for reservoir quality characterization and prediction for exploration, feed development, and production optimization. In addition, Dr. Saju has experience working on integrating the petrographical, petrophysical, and sequence stratigraphic data excuse me, for the carbon dioxide storage site characterization projects, including Chevron Gorgon, CO2, and multiple CO2 CRC projects in Australia. He has considerable experience integrating reservoir quality and clastic diagenesis aspects of rock properties, formation evaluation, well logs, sequence stratigraphy, basin modeling data, petrophysics, geophysics, and geomechanics data, production chemistry and production data within integrated multidisciplinary teams at all stages from exploration and development to production. Dr. Manacheri holds a PhD in petroleum geology from University of Adelaide, Australia, and a master's degree in geology from University of Kerala, India. It is also our proud privilege to introduce him as an alumnus of our institution, as he got his bachelor's degree from Christ College. His professional affiliations are in AAPG, SEPM, and PESA. So with this brief introduction, may I invite Dr. Saju Manacheri for the talk. Over to you, sir.
Thank you, Linda. That's a very nice introduction before my talk. Thank you very much. And I'm very proud and honored to be a speaker for most of the students where I studied and the university. So it's always a pleasure to talk to, especially to the students and to everyone of here. So hope you're all seeing my screen now, and you can hear me well.
Yes, yes.
Okay, thank you. So today I'm talking about the significance of sedimentology in site characterization of geological storage and carbon dioxide. In this talk, I'm going to talk about the experience what I had from some of the projects I'm involved, and I'll talk about some of the issues or the trapping mechanisms in carbon dioxide storage. So you all know. Could you please
I request all the participants to mute your microphone. Yeah. Sir, please go ahead.
We are all talking at the present stage about the global warming, green earth, net zero. You are all hearing all of these things these days. So I would like to take you through this. What are the reasons for the global warming, and what are you talking about the green earth and the net zero in terms of CO2 sequestration, or is it that CO2 is making all the issues on global warming and making the high temperature in the earth and disappearing all the glacial or the ice in the northern and southern hemispheres and making a warmer earth than before? And can we make that warmer earth to a green earth and to make a zero emission of a CO2? So I'll take your attention to first onto the first slide, which is a variation of Earth's surface temperature for last 1,000 years, where you can see in last 50 years of time, the temperature is shooting up, and it's shooting up with like a 0.5% increase, which means like a 2.5 degrees centigrade. It's increasing in like a period of time of 50 years. So this is one comes from the northern hemisphere. If that's happening in northern hemisphere, what's happening throughout the world in the global situation? That's on my second slide, which tells you almost the same. It's last like, I mean, if you look on your x-axis, it's 1980 to 2000. In 20 years time, it's going up. I don't have the last 20 years time temperature. Purposefully, I didn't put it in. You know where it's sitting somewhere there, which means it's going more than 2% of a degree centigrade in that very, very short period of time, which means the global warming is real and we all experiencing that. And what is the reason for that? So from the Global CCS Institute, they provided one of the picture where they're talking about the greenhouse effect, where normally without any greenhouse gases, you see the temperature or the solar radiation is there, but temperature is lower. When there is a natural green gas level goes up, there is a solar radiation, and with the CO2, it goes up. Plus to that, we are giving some sort of additional input of CO2 from our man-made or man-induced greenhouse level, which you can see the temperature is shooting up. That's making the global warming or the earth is unbearable situation to get the temperature in high degrees. Where all this CO2 is coming from? They are coming from the fossil fuels, minerals, natural gas sweetening, cement production, refineries, iron and steel industry, petrochemical industry, and from CO2 biomass. So these are all contributing a higher level of CO2 level in the earth and the global warming. So when you look on the CO2 emission, this is the first one, the first slide, first figure in the slide shows the temperature changes since 1850 to 1900, and the x-axis is the cumulative carbon dioxide emission since 1876. So you see that now where we are sitting is 2020, and already the CO2 emission from the various sources, it's going high. And if you leave that for another 20, 30 years, you can see what's the range, what's the, that profile of the CO2 will be up, and the temperature, what that affects, the temperature will be so high. So then now the industry, now the people, now the government, everyone is thinking of to stop that CO2 emission. So they are thinking of global total net CO2 emission to be reduced and to be make it to zero, net zero. They are targeting to 2015. So they projected from not to emit anything from methane or black carbon or nitrous oxide or any that kind of the CO2 sources to stop it from now. It's 2020 and towards next 30 years time to make it zero. So you can see that's a zero. Then after that, we are not releasing any CO2 to come back. No, we are reducing it still. So that will take to 2100, it will be so down and it's more comfortable in the earth with the temperature. So that's the aim. So we need all these industries. We can't just let it go, the industries, because that's all needs we are looking for. So then what we can do? We can capture the CO2 and you have to hide it or put it somewhere where we can put it that CO2. So that's where we, the people are thinking, the industry is thinking, the government is thinking, where we can keep all this CO2 gas and to capture it or to store it or to be forget it. So that's where my presentation I'm taking to. And my presentation outline, I'm starting with the CO2 geological storage, or how and what we can do, the properties of CO2, and there is a conceptual CO2 storage scenario. And I'm also talking about the trapping mechanisms, where how or what kind of different mechanisms we can utilize the trap the CO2 into different this is a geological trapping rather than any other kind. I'm talking mostly on the geological trapping, like structural and stratigraphic trapping, hydrodynamic trapping, residual trapping, solubility trapping, mineral trapping. Then I'll take you all to different case studies where I was also involved through my experience. I'm not going through in detail, but to show you how we can sequester or to CO2 to put into the storage level and to keep it there, shut it for a long period of time and not to be harmful to the human or to the world. And we finalized with or concluded with CO2 storage projects at present in the worldwide. So what do you need? What do you need for a CO2 sequestration or on the site characterization? The main two things we need is like a sandstone reservoir and a claystone seal. So there is we need a reservoir and to be capped on that. So if you inject into the reservoir and to be capped, so it's like a container you are taking, you're putting something in and put a lid on and seal it. So what are the qualities? What are the main properties we need? All the reservoir rock needs to be more pore spaces. That's the pore spaces where we are injecting our CO2 into it. Then in the seal, we don't need any pore spaces. We ask to be that seal has to be completely filled with or compacted with all the soil or rock or whatever. No space needed to be there. And where we injecting, it's to the reservoir, and the clay stone or the seal rock will be totally capped or trapped, sealed all that CO2. So what are the options for the geological storage of carbon dioxide? We were discussed about like around 6 of them. We can come up with a bit more, but the major six of them I'm going to discuss here. The first one, a depleted oil and gas reservoirs, where the oil and gas is being extracted or explored or produced. Then the area where it's filled with the pore spaces and all of that, so you can inject there, and you know that's a very safe area where oil and gas has been before, and it was been trapped there for millions of years time, no escape or no leakage, nothing. So that's one of the safe place. The second one, which is like a use as a CO2 enhanced oil recovery. This is, applicable in some of the oil extraction or oil production area. You inject the CO2 to push all the other oil towards the production line. And the third one, which is a deep unused saline water saturated reservoir rock, which is, there is no gas, there is no oil, but it's a saline water filled with a reservoir where you can pump into and you can keep it there. The other one is like in a coal mine. If the unused coal mine, you can inject that there, and the CO2 will be used or absorbed or absorbed within that coal layers. The fifth one, again, we can use that CO2 to be enhanced coal bed methane recovery. We can still use as a medium to push all the coal bed methane to recover in the coal intervals. Other areas in suggested options are basalt, where there is cracks and fissures, or oil shales and cavities in limestone areas where you can pump into those areas. So that's all are the options. So now I'm going to talk more about like the depleted oil and gas reservoirs and the deep unused saline water saturated reservoir rocks. So what are the properties? This is a CO2 phase diagram. You can see CO2 be a gas, liquid, and solid, and a supercritical fluid as well. So you can read from that, it's a pressure, temperature on X and Y axis. And we are looking more of that supercritical fluid, which is temperature around 31.1 degrees centigrade and a pressure of 7.38 megapascal. That's where you make your CO2 gas into a liquid, and it's easy to inject into the rocks. This diagram shows about depth, pressure, and temperature. Again, it's like at that point with around 600 meters down, it start to, with the temperature and the pressure, it start to CO2 as a gas going to be liquid. And this is where you are a more critical pressure conditions where it's more of a liquid. So this is telling about the properties. So for the visualization for all of you to understand how that the bigger volume of CO2 as a gas and how that's going to be minimized or to be decreased according to the pressure and temperature conditions. So as the big 100% of like a gas or CO2 will be moving down, if brings down to 800 meters down with the temperature of 31.1 and 7.38 of Pascal, that start to be liquid, and it goes down with even and smaller. So this is a visualization of how we can make a bigger volume of gas to a liquid and to be sequestered into geological formations. So now I'll take you to show some of these storage scenarios. So again, we can inject into some of these homogeneous reservoir. Homogeneous reservoir means high porosity and permeability, where it can be easily distributed and it's be kept on a seal. If it is like, I mean, this is a four-way closure, it's like a dome shape. If it is not a dome shape, it still migrate upwards because of the buoyancy. And these are the structures. And if it is a heterogeneous, where you can see an intermittent sandstone, shale, or siltstone with a porosity permeability variation, this is going to be. I will show you a bit more detail in my next cartoon. So if this is a heterogeneous reservoir with a low porosity, high porosity, more brighter yellow is high porosity, and a bit of brownish, blackish, which is low porosity. So if I'm going to inject the air into one of the homogeneous reservoir, the plume will be moving towards either sides. When I call a plume, which is like a CO2, critical CO2 liquid state, that's a plume. So next one, if I move again, it will be migrating. And you can see how that migration happens. It easily goes through the homogeneous one, and it goes to shorter or not very high efficiency flow or migration into other ones with a low porosity and permeability. So it moves and it moves and it moves and it goes up and up because of the buoyancy. So it stops, and if you inject more, it will go up to there and to a seal area. So now I'll talk about how we can trap all these CO2 as a different trapping mechanisms, in which we will start with all together as a structural stratigraphy trapping, residual trapping, solubility trapping, mineral trapping, all together. I will introduce it and introduce this a picture. On y-axis is a trapping contribution, and x-axis is the time period. So the day one or the year one to 10,000 of years time. So when you start from the day one, most of this trapping will be under stratigraphic and structural trapping. It reduces with the residual and the solubility and the mineral trapping. But while it goes on and on the time, it will be more on residual, solubility, and mineral. So if it is for a longer period of time, it will be captured mostly under residual, solubility, and mineral, and the structural will be lowered or the minimized, which means over time the risk decreases and performances increases, because these are all be permanent trapping rather than it stops there and you feel like maybe it can be leaked. No, it will be permanently trapped during or over the time. So on the structural and stratigraphic trapping, where it's a schematic diagram shows about like the fault. This is a reservoir, and it's been capped by a seal, and that's an unconformity, and that's an anticlinal. Where in the stratigraphic, the reservoir to a reservoir pinching out to a seal, that's where it's more of a stratigraphic trapping. So the reservoir, then this accumulation of the CO2, and it won't be moving because of the seal. So a bit more on the same structural and stratigraphic trapping. This is anticlinal. This is unconformity trapping. This is a fault trapping because of the fault is a sealed one. And if you are looking for the facies changing trapping or the stratigraphic trapping, this is a higher porosity and permeability. And if it goes upwards, it's the permeability and porosity will be reduced. So the trapping mechanism, it's not severe or same intensity. It will be if they migrated upwards because of the shale comes in. So that's more of a stratigraphic trapping. So this one, hydrodynamic trapping, where you injecting into a reservoir unit, and the migration pathways, it's like a 10 to hundreds of kilometers to a structural trapping. It's maybe anticline here, so it moves slowly, and I mean it's like a long residence time through the injection point towards a capping point. So it will take more time to get there, and it will be safe during that migration time. So next one, residual trapping. What is residual? It's keeping or leaving or left some of them on the way when they move. So same like if I'm injecting here, the plume will be moving upwards because of the buoyancy. And you take at a point here, this is where the bluish color, which is, the greenish color, which is more of trap there, and a bit more there, and this is more highly or maximum saturation. So you can see that from the coloration here, CO2 saturations, how that's related to residual trapping. A bit more clearly, you show that while the plume moves towards a up dip direction, it leaves some of this CO2 within these pore spaces of the rock. That's what called the residual trapping. So solubility trapping means like when the plume goes upwards, and then they started to dissolves in the rock itself, and through the process of diffusion, dispersion, and convection, and the density increases, it comes down. So that's how the solubility trapping. So one of my colleagues, when I was working with the CO2 CRC, Ennis King Patterson, they modeled how the CO2 plume injecting in the day one to like around thousands of years time, how that solubility happens. So initially we inject there, it moves upwards, then it stays there for some time, then they started to soluble and started the density, when the density increases, it started dropping. And I mean, in the model for 2,330 years, it comes like a, most of them it's been soluble within the rock and dropped down or gone to lower levels, and it's been utilized. The porosity permeability, it's been utilized, and most of them it's been soluble. So there is no much CO2 to be left. Now they are all CO2 products, maybe dissolution and precipitation and that. So it's safe. Now it's much safer on storing that CO2. So in the mineral trapping, what you can see, I'm going to show you two reservoir, ideal reservoir, which is like a more homogeneous with the high permeability reservoir and with the high permeability and the low permeability. So when you inject the CO2, then it goes up and started to dissolves with some other mineral composition in the rock, then they start to precipitate. Where in the second one, in the heterogeneous, it start moving upwards in the high permeable area, and to the low permeable area, it's also react while they're moving, and it's formed like that. So this is what the cartoon shows. You can see the brown is the grain, and the blue is the pore spaces and water. And you can see the white material, which is precipitating on the grain. So that's also a mineral trapping, which means like a dissolution and start to precipitate on the grains. So this cartoon showing all that together. When you inject a CO2 into a level, it migrates into a anticlinal, or that's a stratigraphic trapping. So that's a structural, and you can see it's completely filled with CO2. Then you look on this area, which you can see dissolution and mineral trapping, where you can see the brine still, it's not coming down, and it's a dissolution and precipitation happens, and the top is like a CO2. Where here, it's a residual trapping. While it's moving, it's leave behind some of the CO2, and you can see that. So with all these mechanisms, if you try to see in time or through time, what happens? In injection, if you are injecting for 10 years time, what happens on the different trapping? Some of them it starts slowly and take in largely and in time. And it's some of them taking within no time, and within 10 to hundreds of years time, it's fill all of that area. Absorption, mineralization, all these things. So you can see how that's picking up. The mineralization, it's take a long time to take it there. That's how all these trapping mechanisms bringing the entire CO to be utilized and keep safe in underground. So now I'm going to talk about like the case studies. So first, I'm talking about a braided delta in a terminal splay complex. You can see a river is coming with a distributary channel to the proximal splay, a distal splay. So the first sample of the sediments, which is more comes from a distributary channel, it's a thick, cross-bedded, coarse, medium sand, basal lag, which has got a high porosity permeability. Then into a proximal splay where it's a small-scale trough cross-bedded, massive ripple laminated sand overlying a thin gravel material. So this has also be a good reservoir for a CO2 injection. Then if you go for a distal splay, you will be meet with stacked sheets of massive and ripple laminated fine sands interlying with the silt and clay. So if you think, if you are hit by a reservoir with a distributary channel to a distal splay, where you are a best reservoir with a distributary channel and a proximal splay, you can inject a good volume of CO2 into that. So that's that sort of sedimentology or the depositional system you can choose for your CO2 injection. So where you see the slide with the blue, which is showing the porosity, you can see a bit more on here. So these all the pore spaces is available for any kind of CO2 trapping. It can be soluble, it can be mineralization. Even if it goes to the shale, it can also a mineral dissolution, solubility, and mineral trapping can happen. So that's how a good braided terminal splay delta complex can be utilized in the stratigraphic record. Another one I would like to introduce is like a Gippsland Basin from Australia on a depleted oil and gas reservoir. This shows like a coastal plain to shallow marine depositional environment with a wave-dominated shoreline. Transitioning from terrestrial influenced sediments and marine influenced sediments. So you can see that's a coastal plain to the shallow marine. So more of a thicker sediment to shallow sediments or a finer grain. So what will happen if you inject in somewhere there? I'll show you another cartoon, which these are the blue ones is migration pathways, which tells you about how the migration happens during time. So again, you can see it may be with all the trapping mechanisms, it been utilized. And mostly you can see mineral trapping within different layers where the higher permeability versus the lower permeability. Still, it's very good on a depleted oil and gas reservoirs. Another one, Outway Basin in Australia, that's also I've been involved with, where you inject into a sandstone reservoir, where you see this is also a depleted gas field. And we put some of the monitors to see how this is moving. So in sedimentology or the stratigraphy, what that tells about like a stacked sandstone bodies varying grain sizes with the shale baffles, sticks deposited near shore, tidally influenced channel settings. So tidal fluvial, the good thick sands, amalgamated channels. So you can inject into all these ones. And these are depleted gas fields. So you know the gas is being safe there for millions of years time. where you can inject into that well, and you put the monitor to see how the migration pathways and how they reach to different levels. Can we identify the time area of CO2 migration? And these are the petrographical thin section slides where you can see blue as a pore spaces, and you can inject into those areas. So these are the different grain sizes, coarse to very fine sand. In between, there's a good amount of porosity. It's been, characterized in the sandstones. And again, the model, which they tells you about like the trapped CO2, and it's a free CO2. So it's more of a residual trapping can be utilized in here. But later, it can be more of a mineral or a solubility trapping can also be proposed in these ones. The next one, the Gorgon CO2 injection projects. That's one of them. I lately enjoyed my work with Chevron, where we are injecting into a late Jurassic Dupi formation, consists of sandstone and siltstone in a deep water slope depositional settings. This is a very good reservoir, the lower Dupi, and a massive upper massive sand with a very silty bit of clay and all of that. And this is a cartoon showing how the deep water slope at deposition settings. So it goes upwards, and there is a upper Dupi, which can be or a regional shale, barrow group shale is there to cap all of that. So when we characterize that, we saw a good amount of pore spaces or a better porosity permeability conditions where it can be residual solubility or mineral trapping mechanisms can be utilized. That's how we can keep all these CO2 safely into these formations. So with some of the engineers, while I was working, they model the CO2 plume movement or migration from the point where they are injecting in through time. So they model that. I would like to show that as well to you all. So when after the injection, the year 5, after the 5 years time, the green one, which shows you the migrated the movement of the plume is. So you watch on this area as well as this one. This is like a seismically, or they are showing what in the plan view, how the plume is migrating. So next one, in year 10, you see that. In year 20, you see a bit more on lateral as well vertical migration. In year 40, you see a bit more or the larger amount of migration towards your spatial distribution, or spatially it's moving rather than the vertical, it's horizontally moving. But again, it's also moving vertically as well. And it seems to be in 65th year. Then it goes to 1,000 year, and it goes to 500 years. So see, we almost stopped the pumping or the injecting CO2, but still you can see the area where we injected is more of residual, and the plume is moving towards to an upper dip situation to be trapped as a structural or stratigraphic trapping. So next one, if you look on the 1,000 years time, it's all goes up and it's more concentrated in the area where it's a structural trapping or stratigraphic trapping, and it's towards the air seal area. So another one I would like to show you from the Sleipner gas field in North Sea. They started like when we did in Australia. So they already started injecting in 1999, and they monitored seismically how the plume is moving. And in 2001 and 2002. So that's a vertical or the seismic one sections. And this is like, a plan view to see how that plume is moving differently or moving spatially to see and how we can monitor. So that's also been applied to show, because of our good stratigraphic correlations, to show how the plume is moving. We can monitor, and it's safe to inject into all these CO2 CO2 to be injected into these sandstone reservoirs. So by that, we will move to see the new projects worldwide. Now, the government, the people, the companies all are so interested, and they are well equipped with all the latest technology to be capture the CO2 and to be injected into the geologically injected into the sandstone reservoirs. So you can see from America, that's like a monitoring project in Derby Scanfield, Illinois Basin in America, in Japanese Nakawaka, then Sleipner, another one, Utsira formations. That's like a UK Southern North Sea, in Denmark. Then you can see it's from Germany. You can see from China, and they are moving Norwegian continental shelf. So everywhere people are, or the companies are, or the government is more interested, and they are joining to cope to the present situation to reduce the CO2 emission, and looking forward to a green earth or net zero. That makes CO2 to be capped, or like to be not to be released into the environment, to get a more global warming and to a better safe place for the human. By that, I'm finishing my talk. Thank you very much for attending and hearing my talk. So now it's a time for question and answers.
Thank you, Dr. Saju. It was a wonderful presentation. And I'm sure that many of the students, they have found it very interactive and interesting, as we see a number of questions already in the chat box. Probably you can read it out, or shall I read it out for you?
I will try to read it one. So it's a Govind Joshi is the first one, I think.
Yeah.
How does post injection effects such as destabilization of subsurface strata can be taken care? Do you any possibility of seismic activities can be expected? Not really. The seismic activities, like, I mean, we initially we are injecting into the depleted gas or oil reservoirs, as well as like deep saline reservoirs, where it safely can be injected and to be trapped with the different trapping mechanisms. So we don't see much of any of the last 20 years or more. We didn't hear any kind of seismic activities. But in some places like France, Germany, what they are planning, they are injecting into a container. It's not geologically, but like, I mean, in a shallow area, into trap that. But again, there are some of the news has come out, but again, I don't believe if you are injecting that into a deeper depths, it won't be a problem. Hope Govind, that's answer my answer your question. If not, send me another question or not. To Johannes Nuara, good evening, Saju. After the CO2 is injected into subsurface, how do we know exactly the percentage of contribution of each trapping mechanism specific for our injection site and reservoir? Also, its solubility trapping a natural process or something that engineers can improve and manipulate? That's a good question. That's a great question. Again, if the trapping mechanism, that's what I showed in one of the diagram. Initially, it more of trapping on stratigraphic or structural trapping. All other will be when they start, it's less. but in time it will be higher. And on mineral trapping, it's a natural one. If you are injecting CO2, CO2 is going to be dissolved in the saline water, and according to temperature and pressure, it will be different on dissolution or the solubility of the CO2. Once the CO2 is soluble, it's goes to be more of acidic nature, carbonic acid. So that's going to dissolve mostly the feldspar and clay minerals. Then it start to precipitate to make the mass balance. So it's trap the solubility, and then it will be trapping as a mineral precipitation. And the engineers, yeah, definitely the engineers can do that according to the when they understand the solution or the saline water and the pressure condition, temperature condition, you can use that entire knowledge to increase or decrease of that plume or critical, supercritical CO2 in such a way that it be mostly dissolvable in that reservoir condition. Yeah, they can do a better way to get more solubility within that saline water or saline reservoirs. Other one, how does the quantity of liquid CO2 is be decided? That's another good question. So again, we calculate on reservoir condition, what is the porosity and permeability, and how much of that can be utilized. So for example, if I say 100 megaton, and is it that we can inject into the available pore spaces? Then it's easy. Always we inject less amount with the volume, the porous volume in the reservoir. So that can also be easily, we can find out, and we can utilize the information to decide what is the percentage of liquid CO2 to be injected. If we compare variety of deposition environments such as turbidite, fluvial, deltaic setting, which one is the most effective for CO2 storage? If I'm blindly say it's more of a fluvial deltaic, which always have a higher porosity and permeability, where less, you will get a more of feldspar and more of the residual trapping will be higher, and it will be react with the composition and to make a more of mineral solubility and mineral trapping. And also you can get a better stratigraphic as well as the structural trapping as well in fluvial deltaic settings. And they are more of a thicker ones and the shale, on the shale or the clay or seal area. So that's all I think. Is there any other ones? I missed anything?
I think there is no other question.
Okay.
I do have a question. If it is
okay,
allowed.
Thank you.
Yeah, it's about I just want to know, while injecting this carbon dioxide into the substrate, do we have a chance of reducing the subsidence? Suppose we have heard that many places where the water or natural gas or even petroleum has been extracted, that area undergoes subsidence. So can it be used as a mitigation for subsidence?
It is. That's where, I said it's EOR, enhanced oil and gas recovery, where they're injecting. So what you're taking out, you can inject back and to keep that pressure there. So there won't be such a subsidence. Yeah, that's another way of doing it. Like something you are taking out, something you are to pumping in, and that's be stabilized there. So they are using the EOR, enhanced oil recovery or enhanced gas recovery, where it's injecting into that and keeping that more safer rather than any subsidence or any structural disturbance or as Govind asked, like the seismic, any issues there. So we can keep the balance there. Yeah.
That's great. Yeah. And thank you very much.
Thank you.
since it's already our time now and we don't have any other question, I thank you very much on behalf of all the participants. It was truly a wonderful talk. I'm sure that many of you have benefited. It's time to go for the next speaker. Now I invite Dr. Vetrimurugan Ermalai, professor from University of Zululand, to introduce the next speaker. Vetri, over to you.
Thank you so much. Good evening, everybody. I thank Dr. Lindo for giving me this opportunity to host these sessions. This session is on developments in hydrology. I would like to introduce our guest speaker of today's sessions, Ms. Lali Anil. She's a hydrogeologist and hydrogeochemist working in Innova Consultant Limited company in Canada, which is one of the world's leading independent specialists providing of environmental testing and analytical services. They are working with so many countries, European and American countries. Ms. Lali Anil started her hydrogeology career in Kerala groundwater department from 1996 to 2001. One of the apex institutions that conducts the investigations, development, and management of groundwater resources of Kerala. Another wonderful experience worth mentioning is that she is actively involved in the first phase of the World Bank aided hydrology project aimed at generating hydrological information systems for India. The next 5 years of her service was carried out with Kerala State Land Use Board between 2001 and 2006 in India. She has overseen a Rajiv Gandhi drinking water mission projects, preparing groundwater prospects maps for KSREZ using GIS tools. She has led a multidisciplinary project on the impact of Tanir Mukkam barrier on the Kuttanad wetland ecosystem. She has generated a digital map for the hydrology project from groundwater department in Kerala. Ms. Lali Anil is a registered professional geologist with the Association of Professional Engineering and Geoscientists of Alberta. She holds Master of Geology in 1991 from the University of Kerala, Thiruvananthapuram, in India. She did diploma in remote sensing and GIS 2003 in Kerala State Land Use Board and AGES Thiruvananthapuram. She is going to give her presentation on hydrogeology and groundwater issues of Alberta, Canada. Dear colleagues, please mute your video and microphone all the times. When it is your question time, please unmute for your microphone. If you need, you can unmute your video also. Please enter any questions you may have in the chat box at the right corner. You may enter question during the presentation also. Finally, now I welcome Ms. Lali for the talk. Ms. Lali Anil, it's your time now. Please go ahead with your presentation. Thank you. Can you hear me, Lali?
Yes. Thank you.
Okay.
Hi, everyone. Let me share my screen.
Yes, please.
Hello, everyone. And thank you, Professor Vetrimurugan, for a nice introduction. So there was a small correction. So currently, I am not working. due to the COVID, my company has been like closed. So my experience was mostly, I was engaged with the environmental consulting companies here in Alberta, not with Illinois. It's a mistake. Sorry about that. And first of all, I would like to thank the organizers and especially Dr. Saju Manacheri for this nice opportunity to share some of my experiences in hydrogeology with the students and the other professionals. So my topic will be mostly a general topic, intending to give some information to the budding geologist, the next generation geologist. So let us see, and before we start, let us let me share one thing. Actually, me and Saju were classmates during our MSc at the University of Kerala, Karyavattam. And I also thank everyone for attending this presentation and are still patiently here. So let me move on to the first. Today we are going to talk about the hydrogeology and groundwater issues of Alberta. I started my career in Alberta in the year of 2006. So here you can see a list of the topics I'm going to cover today. So I'll be touching the geology, hydrogeology, groundwater quality of Alberta, following a brief introduction and a conclusion at the end. So let us see the location. To start with, let us see the location and the geographic boundaries of Alberta. So as you see in the picture here, the Alberta is located on the northwestern part of Canada. And it is bordered by British Columbia to the west, Northwest Territories to the north, Saskatchewan to the east, and the United States of America to the south. So these are the main cities in Alberta. Edmonton is the capital city. Calgary is the city we are residing. And this is the Fort McMurray, where most of the oil sand operations are happening. So these are the longitudes and the latitudes of Alberta. So geographically speaking, Alberta is located in the west longitudes 10 and 120 and north latitudes 49 and 60 degree. So, so you may be wondering what this Saskatchewan meridian is. So you see Saskatchewan is the neighboring province, the the province to the east of Alberta. So if you see the fourth meridian shown here, this is the longest surveyed line, straight line on Earth. So now let us move on to the climate of this region, because climate always play a major role on the life of Albertans and as well as the water resources here and as well as the business. Everything, the climate matters a lot. So when we speak of climate, this is the best place to experience all the four seasons. So we can see all the four seasons very clearly. We can experience it very clearly as you see the beautiful pictures here. So in Alberta, the spring starts from March to May. So this is the spring, the pictures of the, you can see the springtime. And these are the activities. So the spring activities, this is the spring activities after the winter, long winter, the people started like enjoying the sunshine outside. This is the time when the snow starts to melt and the temperature usually rises. Spring time is followed by the summer season. Summer season starts from June to August, or sometimes it extends to September. The average daily daytime temperatures are usually in the range of 16 to 20, and it may reach up to 30 degrees or even higher in July. So that, as I mentioned before, the life of our Albertans are highly influenced by the weather of Alberta. So everything like the food, the dressing, the driving, everything is for every season, and the business also. After summer, we see fall. This is a very beautiful time. It's a very good tree to the eyes, because you see, when the in the fall season, that is the autumn season, it's the time when the temperature starting to slow down, and the leaves will be like changing colors before before they shed the trees shed the leaves. So it will be a great tree to the eyes actually. So these are the winter the fall activities, like raking the leaves from the ground. And next is winter. Winter usually starts from December to February, or even extends later in March. But most of the time in Calgary, the place where we live, what I have seen is that the winter starts from the mid of October, even earlier, the mid of October, November. So the winter is the longest time here. So what you see here is a list of terms we will be referring during this presentation. So what I'm planning is I would mention these, introduce these terms as and when it comes. So let us start with the water resources. So we all know that water is a natural resource, and it is a life supporting resource. And we see water resources on the surface as surface water, groundwater, or as ice in the glaciers. It is also a renewable resource, and it can be replenished through the water cycle. So coming to the water resources of Canada, 20% of the world's freshwater resources are located in Canada, and of which 2.2% of the total freshwater in Canada, Alberta has 2.2% of the total freshwater. So we will discuss these things later. So what is the role of water cycle in replenishing the water resources, or replenishing the water resources of a region? The water cycle, which is also called the hydrologic cycle, is an endless circulation of water between the earth and the atmosphere. So as you see, the water from the land and the ocean escapes as evaporation and evapotranspiration and reaches the atmosphere. Once it reaches the atmosphere, it condenses and forms the clouds. And the clouds then move towards the land and forms the precipitation. The precipitation that falls on the ground goes either as surface runoff, and a portion of it will be like infiltrated into the ground and form part of the groundwater storage. The surface runoff, as it moves down and it also dissolves the nutrients and the minerals that comes in contact with the soil, from the soil that comes in contact with the soil and the rock formations. So what it means is that the water cycle plays a main role in replenishing the water resources. Either it is surface water or groundwater or the ice in the glaciers. Now let us see the surface water resources, because we know that before coming to the topic of groundwater, because all these forms part of the water cycle, they play a great role each other. So Alberta has 7 major river basins. So these 7 major rivers contribute to the surface water resources of Alberta. So we will see most of the rivers in Alberta starts from the Rocky Mountains on the west. So the important ones are the Hay River Basin, this one, and this one is the Peace or Slave River Basin, and this is the Athabasca River Basin. These 3 are the north flowing rivers. So these 3 north flowing rivers flow and ends in the Arctic Ocean. It starts from the Rocky Mountains, travels through the Alberta and ends in the Arctic Ocean. And these 3 major rivers constitute more than 80% of the water resources, surface water resources of Alberta. Next comes the east flowing rivers, that is the Beaver River Basin, North Saskatchewan River Basin, and South Saskatchewan River Basin. So except these North and South Saskatchewan River, the Beaver starts from a Beaver Lake. It's not from the Rocky Mountains, but on the other hand, these 2 are starting from the Rocky Mountains. And that moves to the east and ends in the Hudson Bay. The last one, the one at the bottom that is on the southern side, is the Milk River. Actually, it's also starting from the Rocky Mountains, but from the USA, United States of America. So it starts in the United States of America and then enters on the southern part of Alberta, flow to the east, and again flows down to the USA, where it confluences with the river Missouri and finally ends up in Gulf of Mexico. So what do you see here? Sorry. So what you see here is the distribution of water in Alberta. So as you see here, the north flowing rivers constitute more than 86.6% of the surface water resources, the east flowing 13, and the south flowing, that's a small river, that's only 0.1%. This is a picture of a Red Deer River that is a tributary to the South Saskatchewan River. As you see here, the meanders of the Red Deer River, this is how the landscape looks like in here. And also the broad floodplain and the foothill regions you can see on the extreme side of the photograph. Oh my God. Oh my goodness. So here you see the physiographic regions of Alberta. Physiographically, Alberta can be divided into 4 major divisions. It's Canadian Shield, interior plains, and foothills and Rocky Mountains forming the Cordillera region. So this is the Rocky Mountain region, and the area marked with F is the foothills region, and the C is the Canadian Shield region, and the rest is together grouped as the interior plains. So this table shows what is the geology of each region. So as you see, the Canadian Shield region has granite, gneiss, quartzites, and sandstones. The interior plains is characterized by sandstone, shale of tertiary age, non-marine sandstone and coal of marine and marine shale of upper Cretaceous, shale and oil sands in the lower Cretaceous. So all are concentrated in the interior plain, and limestone, dolomite, and salt and gypsum of Devonian age. Whereas when you come to the foothills, the Cordillera region comprising the foothills and the Rocky Mountains, so it has Precambrian, Paleozoic, as well as Triassic, Jurassic, Cretaceous, the rocks forming to all these age groups. So it is a combination of limestone, dolomite, shale, quartzite, sandstone, shale, carbonate rocks, etc. So these are some of the pictures of the how you see in nature here in Alberta. So this is a picture of the interior plain characterized by the rolling topography, and this is the boreal forest regions. So the boreal forest regions are the upper portions, the northern part of the Alberta. And this is the foothill region characterized by steep-sided hills, then Rocky Mountain in summer, and Canadian Shield region in Alberta. Now, let us move on to the geology of Alberta. So the geology of Alberta can be broadly divided into two. It's the superficial geology and the bedrock geology. So the deposits that is above the bedrock is together classified as the superficial deposits. It comprises the pre-glacial deposits of Paleogene to Neogene age, followed by the Pleistocene glacial deposits and the Aeolian deposits and the recent deposits of that is the modern environments, present day environments. So the next few slides, you will be like seeing the pictures and a brief description of all these superficial deposits. So I'm not going to explain those things. These superficial deposits makes it's very important for the hydrogeology part, because most of the 16% of the wells are located in the superficial deposits. So these are the superficial deposits of Holocene age. So as I mentioned before, it's the present day environments of the modern glaciers. Organic deposits, this will be usually seen in the northern part of Alberta, especially in the boreal forest regions, characterized with the marshes, swamps, and bogs. Then the colluvial deposits on the slopes and valley slopes or the hill slopes. This is also the Holocene deposits of river alluvial deposits, and this is lacustrine deposit. These are all pictures from Alberta. And this is a Aeolian deposit of Pleistocene to Holocene. It includes both active and vegetated dunes and sand sheets in Alberta. So this is the most important parts. Most of the glacial deposits, most of the superficial deposits in Alberta belongs to the glacial period. It's deposited by the continental and the valley glaciers at the time of retreating. So these are the glacial deposits. It includes glacial lacustrine deposits, as you see in the picture here, fluvial deposits. So here what you see is not a sorted. You can see grains of different sizes ranging from clay to boulders. And this is moraine deposit. So these things we see in the fluted moraine deposit usually see in the northern part. This also in the northern part, stagnant ice moraine, and the last one is the ice thrust moraine. So what you see here is the below the superficial deposits, you see the bedrock. This is the bedrock geology of Alberta. So here is an interactive map link. So if we go to the interactive map link, we can see what are all these formations. And so this is the Rocky Mountain region. Each color represents each formation. As you see here, this is the Canadian Shield region with the granites and those, and also the sedimentary rocks over here of Precambrian age. This table of formations is a continuation of the other one. The other one is a spatial representation. This is a tabular representation of the geological formations in Alberta. As you see here, this is an index of, so what is shown in this column is belongs to this part of the Rocky Mountain region. And this is this stratigraphic column is here. And so we will be concentrating more on the upper portions because that is the productive, most productive aquifers are concentrated in here. So we will see the geology in detail as we proceed. So as I mentioned before, these are the key terms we will be using during this presentation. So I made a table for you guys to understand easily. So from this table, we can clearly see this an aquifer formation is characterized with porosity and permeability. Permeability means the pore spaces are interconnected and the water can flow through the pore spaces. So because of that, an aquifer formation can yield water sufficiently. A good example of an aquifer is a sand and gravel deposit. Then what is an aquitad? Aquitad has porosity, but it doesn't have permeability as in aquifer. It will be reduced permeability. So the result is it can yield water, but it cannot yield enough. So a good example is a sandy clay. The next one is an aquiclude. So here what you see is an aquiclude has porosity, but it is impermeable. The pore spaces are not interconnected, and because of the same reason, it cannot yield any water. A good example for an aquiclude is a clay. The last one is the aquefuge. We won't be referring this much of this term in the presentation, but it doesn't have any porosity and it is also impermeable. So since it cannot hold any water or it cannot transmit any water, naturally it won't yield any water. So in some region, but all these are referring to the primary porosity. But there is another term called the secondary porosity. This aquefuge can hold and permit water if it is fractured and fissured, and the fissures are interconnected. So now we will see another two terms, that is confined and unconfined aquifer. So as you see here, you see aquiclude and aquefuge, and this is an aquifer. So when a water-bearing formation or a rock unit is sandwiched between an aquiclude and or aquefuge, or sandwiched between two impermeable layers, it is called a confined aquifer. So a confined aquifer is usually recharged through the area where it exposed to the surface. So if you put a well in a confined aquifer, the water will rise above the upper level of the confined aquifer, because the pressure in the water, the pressure of the water in the confined aquifer will always be higher because of this confining property. And above the above the aquiclude, you see unconfined or water table aquifer. So as the name indicates, it is not confined by an upper layer. So the water level in the unconfined aquifer or a water table aquifer, as you see when you dig a well in the unconfined aquifer, the water level in the well will be the water table of that region, representing this. So the water pressure, this is at the water level, means the water table, the atmospheric pressure will be the same as the water pressure. So now let us move on to the different types of aquifers of Alberta. Two main types of aquifers are seen in Alberta. As we described the geology, the aquifers are also classified as surficial aquifers and bedrock aquifers. So as the term signifies, surficial aquifers are the aquifers the water bearing formations in the surficial deposits, and the bedrock aquifers are the water bearing formations in the bedrock formations. So if you see the amount of water available in each type, the surficial or the bedrock aquifers varies depending upon the geological makeup of the area, because we saw different types of aquifers. It can be sand or gravel or sandy clay or clay like that. And 84% of the water wells draw water from the bedrock aquifers, and only 16% is in the surficial aquifers. So let us see the surficial aquifers a little bit in detail. So the surficial aquifers usually have thickness from ground surface to 10 to 30 meter below the surface, and it constitutes the best surficial aquifers constitute the sand and gravel deposits. And there is another type of surficial aquifer in Alberta. It is called the buried valleys. It is a vast network of valleys carved in the bedrock by fluvial and glaciofluvial or glaciolacustrine actions. So these buried valleys, where it includes the glacier valleys as well as the pre-glacial fluvial valleys. So you can see extensive deposits of sand, gravel, silt, and clay in these buried valleys with a thickness ranging from 30 to 300 meters and a width from 0.4 kilometer to 16 kilometers. So now you can imagine the size of these buried valleys. So the hydrogeology, the buried valleys in Alberta has not been surveyed completely. So we don't have a good information, complete information on the buried valleys yet. The studies are still continuing. These are very good potential aquifers in Alberta. And these forms the excellent sites for high yielding wells produce up to 500 gallons per minute. This is a picture of the surficial deposit that forms the aquifer in Alberta. This is a pre-glacial gravel deposit. So that's a fluvial deposit seen in the central part of Alberta. And here you see another few photographs. So here you can see the contact between the bedrocks and the sediments over the bedrock. So this hazy color shows, and the layering is identified with the bedrock, and you can see there is not much layering or you can see on the surficial deposits above the bedrock. And here is another most productive aquifer in Alberta. It is called the sandstone of Pascafu formation. So we will be referring these terms later. So, and this is the surficial deposits above the Pascafu aquifer. This photograph is, you can see coal within a scollard formation. This is a formation just seen below the Pascapu formation. So you can see the layering of coal in this picture. So what you see here is a conceptual model of the surficial aquifers in Alberta. So as I mentioned before, the surficial aquifers constitute the sand and gravel deposits, silt and clay deposits. So clay is actually not an aquifer, but these are the surficial geology actually. And below is the bedrock. So if you see the hydraulic conductivity, so hydraulic conductivity is the ability of a porous medium to transmit water. And the hydraulic conductivity determines how well these aquifers can transmit water and yield water. So if you see here on the x-axis, the sand and gravel deposits have the hydraulic conductivity, higher hydraulic conductivity. That means the water bearing property increases as you move from left to right. So that means you can see from clay, silty clay, silt, fine sand, sand and gravel. So the hydraulic conductivity is increasing. So now let us move on to the bedrock aquifers of Alberta. The bedrock aquifers, the three main types of bedrock aquifers in Alberta, they are sandstone aquifers. They are highly permeable and can yield either fresh or saline water. Next one is a carbonate aquifer characterized with the limestones. Most of the water in the carbonate aquifers are saline waters and has high TDS values. TDS means total dissolved solids. The next one is a shale aquifer. We know shales are usually doesn't have primary porosity will be very less. So when the shale become fractured and fissures and the fractures are interconnected, they can act as good aquifers too. Alberta has variable, the shale aquifers in Alberta has variable yields depending on the degree of the interconnected fractures. Here you see a model of the bedrock geology of Alberta. So as I mentioned before, these are the main formations that is important to the water bearing or the groundwater importance. The top one is the Paskapu formation. It is represented in the yellow color, followed by the Scolad formation. Then it is Horseshoe Canyon formation, Bear Paw formation, Belly River formation, and Lee Park formation. So this all the formations above the Lee Park formation is non-marine, whereas this one is a marine formation. So what we can see is when we put a well here, the water quality of the water quality decreases downwards. We can see that the total dissolved solids and the hardness of the water increases as we go down. So, and if the rocks are going there is a chance of too deep, there is a chance of meeting the saline water also. So among all these aquifers, Paskapu is the most productive aquifers in Alberta, followed by the next one is Scolad and the other one is Horseshoe. There are very few wells are located in Bear Paw formation and Belly River groups. Here you see a cross section of the formations in Alberta. So this, as you see here, this is close to the Rocky Mountain region, and as you move to the east, you can see the formations. The other formations are like outcropping. So, and it has a general dip towards the Rocky Mountain. So as we move further to the east, these formations are of like upper Cretaceous, but the lower Cretaceous deposits in Alberta carry most of the oil sands. So as we move to the east, what I meant to say is the oil sand bearing deposits will be outcropping. So that is why we have like open cast mining of the oil sand deposits here. So this is the hydraulic conductivity of the formations as we see here. So Paskapu has the highest hydraulic conductivity or the good aquifer properties, followed by, so all these are sandstone formations. The difference is the grain size and the cementing medium changes. So the grain, compared to the Paskapu formation, the Scolad has smaller grain sizes. Similarly with the Horseshoe Canyon formation, and there are like carbonaceous materials and shale clay interbedded in between all these formations. Now let us see the lithology of different formations and their expected yields. So as I mentioned before, these are the formations we in Alberta. The Pascapu formation is characterized with a sandstone, siltstone, and mudstone. And the sandstones usually yield like, 1 to 500 GPM, depending upon the grain size, the cementing medium, etc. So this is a classification based on what you see on the different physiographic regions that I mentioned before. This column represents the rocks in the interior plains, mountains and Rocky Mountains and foothills are grouped together here, and the Canadian Shield of Northeast Alberta. So of all these, sandstone is the best productive aquifer in Alberta, and that is from the Pascapu formation. And also there are sandstone and mudstone in this Collard formation, Battle formation. So these formation names varies from place to place. Once you move to the east, we can see another names with that is equivalent to Pascapu formation, Collard formation, and Battle formation. I'm not mentioning all those things in here because we won't be able to finish in half an hour then. So as you see here, the dolomites and limestones are mostly concentrated in the Rocky Mountain regions. You cannot see much of the limestone dolomite formations in the interior plains. It is mostly in the mountains and foothill regions. So what this discharge shows is 30,000 gallon per points. These are the points of discharge of the springs. This is where the spring appears. So that is why the discharge is too high. As we mentioned before, clays are not good aquifers, so it cannot yield much water. But this sand and gravel forms the deposits in the buried valleys. See the yield here, it can range from less than 1 to 500 gallons per minute. So now let us see the groundwater resources of Alberta. So the groundwater resource, Alberta has approximately, it is estimated that approximately 40,000 cubic kilometers of water in Alberta. That is the groundwater resources. So a large quantity of this groundwater is occur in the bedrock aquifers and also in the buried channels. So coming to the water use, most of the Albertans rely upon the surface water for their drinking, but only 21% of the total population, that is approximately 600,000, is depends on the groundwater resources for their drinking purposes. So if you see the groundwater allocation in Alberta, of the total groundwater resources available, only this much is licensed for use in Alberta. So of which the major share is used in the industrial sector, followed by the agricultural field, 23%, and followed by 19% in the municipal sector. The rest is very less. So this picture also indicates the groundwater impacts. So who will be causing the most impact to the groundwater resources in Alberta? Definitely it will be the industrial, followed by the agriculture and municipal activities. So what you see here is groundwater resources and quality. How much water we have. We saw how much groundwater resources we have and what is the quality, because it is a life supporting resource actually, groundwater. So it is an area of main concern, how we use the water and how for do we have a sustainable quantity? So ensuring a sustainable quantity and maintaining the quality of the water resources is a very important point. So as we see in the previous discussion also by Dr. Saju Meenacheri, so there was a reference like the land subsidence. So in groundwater case also, it can lead to land subsidence under what condition? So when we remove water extensively from the aquifers underground, so it results in the overdraft conditions. So how do you see it here? When we measure the water table, you see the water table is naturally going down and down. That means there is a decline of groundwater level. So when there is a decline, that means the aquifers are depleting. So once the water that is stored in the pore spaces has taken off, what happens? These spaces become vacuum. So there is a chance of land subsidence. There are certain cases in, I believe in India, there is a land subsidence, especially in the West Bengal region. So another quantity, the water quality, the quality of water also play a major role in the quantity. How? Because when water loses its quality, the overall quantity of usable water is also decreased. So that also impacts the quantity of water that can be used for drinking or domestic purposes or other uses. So also, now coming to the quality of groundwater, the quality plays a major role on the overall health of our human beings, because so we drink water, so if the quality is not good, that affects our health adversely. Where these the contamination or the quality deteriorating factors or the chemicals are coming. So there are natural sources as well as man-made or anthropogenic sources or processes. For example, the natural sources are the, as we mentioned before, when water travels through the soil and rock columns, it comes in contact with the different types of minerals, and based on the local geology, and we all know that water is a universal solvent, so it dissolves some of the minerals and from the soil and rock, and this way the chemical content of the chemical property of the water will change. Also, the anthropogenic sources will be like, when there is a use, there is a waste actually. So landfill sites, industrial waste, agriculture, septic field, etc. Example is agricultural nitrate input and bacterial presence in groundwater. So at this point, I would like to mention one more thing. So the source of water contamination can be broadly divided into two, whether as point sources as well as non-point sources. What is the significance of such a classification is that when we come up with the remediation activities, it is very easy to contain the contamination and like do the remediation activities if it is a point source. For example, landfill site is a good example of a point source. So we can control it, we can see from where it comes. But for a non-point source, just as like the source from the geologic materials, you cannot contain it. So that means the remediation process of those natural sources, contamination in groundwater is bit harder than the man-made sources and that are point sources. So the contamination can be how the contamination changes the quality of the water. So it can change the chemical quality, the biological quality, as well as the inorganic, organic, and microbial. So the inorganic constitutes to the chemical ones. It includes the heavy metals, nitrates, fluoride, etc. And the organic contaminants will be the hydrocarbons mainly, as well as the pesticides and the pesticides we use in the agricultural field. And also microbial contaminants from the landfill sites, etc. for an example is a coliform bacteria. Next is how is groundwater use regulated in Alberta? So as we see here, all the water in Alberta is owned by the Crown and managed by the province. So regardless of whether it occurs on public or private land. There are two acts that regulates the water use in Alberta. The first one is Water Act. So it regulates the withdrawal, diversion, and use of water, irrespective of whether it is surface water or groundwater. So this Water Act is applicable to both surface and groundwater. So if you do like a withdrawal or diversion activity, so you need a license from the government, and it needs to be licensed, and it needs to be approved by the Alberta environment. So for household and other traditional agricultural uses, not the traditional is not same as the business level of agriculture. For business level of agriculture, definitely a license is required, but for a traditional small agricultural activities and household activities, normally a license is not required. And next is the Environmental Protection and Enhancement Act. So what it does mainly is it regulates the activities that adversely affect the water quality, irrespective of whether it is surface water or groundwater. It includes both actually. So when we during the business we know that the business activities, the agricultural activities, and the municipal activities releases waste, and these waste, there is a chance of contaminating these the groundwater resources locally. So this act regulates and keep monitoring the activities of the major companies, drilling activities, oil sand production, etc. The next one is, yes.
You got a more slides there. It's like a 12 minutes over now.
I have it will be done soon actually. It's not many actually left.
Okay, no worries then. Thank you.
Okay, thank you, Saju. So these are some groundwater quality key terms. So what is natural groundwater quality? When we talk about the natural groundwater quality, it constitutes the physical, chemical, and biological quality of the usable water. And the physical quality, what are the factors? Temperature, turbidity, color, taste, odor, pH, etc. The chemical quality mainly constitute the major ions and minor ions, and the nutrients and trace elements. The major and minor ions constitute more than 99% of the ions in water. The trace elements constitute only less than 1% of the total ions present in water. So coming to the biological quality, the microorganisms, it is the bacteria, viruses, and other seen in the water. It is invisible to the naked eye. So natural contaminants. So as we see before, it causes the potential health effects as well as aesthetic quality of water. So the major potential groundwater contaminating activities in Alberta are, as I mentioned before, it is agricultural impacts. So from nitrate leaching, pesticide leaching, and manure management. Then industrial impacts, industrial waste management, mining activities, spill management, leaks from faulty structures, etc. When municipal impacts like landfill management and lawn fertilizers, de-icing, and this is another important in the communities, de-icing and salting during winter. So here you see a table of the guideline the government of Alberta is using to monitor the groundwater quality here, and these are the different ions, the major and minor ions. And as you see here, most of the major ions are not normally causing any health effects to the groundwater quality in terms of drinking purposes. So whereas the minor ions, the fluoride causes chronic health issues, nitrate causes acute health issues, etc. And the next one is trace elements. So most of the time, the groundwater quality harmful to the health or causing health concern is the trace elements in water, as you see here. The next is we focus on two cases of groundwater issues. There are, as I mentioned before, there are so many other cases, but I am taking only two. The elevated nitrate levels in the shallow aquifers of Alberta and the fluoride in groundwater. So as I mentioned before, over 90% of the rural Albertans rely on groundwater for drinking purposes. The health effects of a nitrate, higher levels of nitrate in drinking water is, if it is over 45 milligram per liter, it causes severe health concerns. From where the nitrate comes, it's mainly from the agriculture, the fertilizers we use in the agriculture. And we will see the spatial distribution of nitrate levels in Alberta and nitrate occurrence by geologic unit and source of nitrate in groundwater, followed by the fluoride in groundwater. So as we see in this slide, there are a few questions. So you may be like, what is it? What is nitrate? So it's a common form of nitrogen, usually see in water. It comes from soil, water, and plants. The important thing is what nitrate is water soluble and stable, and it do not evaporate. So if you boil water, you cannot reduce nitrate content in water. So boiling is when drinking water is contaminated with nitrate, you cannot remove nitrate by boiling. So actually the boiling will increase the nitrate content in water. And what are the nitrate sources in water? It can be natural sources such as through precipitation, leaching of organic debris, etc., or through human activities like fertilizer application, animal production in feedlots and livestock waste, etc. How could nitrate affect your health? That is the most important thing. Higher levels of nitrate in drinking water can cause methemoglobinemia in adults. It's a condition when the nitrate reacts with the hemoglobin, or nitrate changes the hemoglobin in the blood to methemoglobin. So what happens is, when the hemoglobin is converted to methemoglobin, the oxygen content in the blood stream decreases. So in kids, in babies or infants, it appears as blue baby syndrome. So how you can say is the baby's skin turns into bluish color, particularly around the eyes and mouth. The high methemoglobin levels can also lead to digestive and respiratory problems, anoxia, brain damage, or even death. But those are very, very rare cases, but these are reversible, or these are treatable conditions once it is recognized. So who are the most vulnerable group for higher nitrate levels in drinking water? Especially pregnant women and infants. And what is the guideline? So as we saw here, it is the the Alberta groundwater drinking water quality guideline. As per the drinking quality guideline, the maximum permissible concentration in drinking water is 45 milligram per liter. So here you see the spatial distribution of the nitrate in Alberta. As you see, most of the wells are located on the southern Alberta because these are the most populated areas of Alberta. The northern Alberta is not that populated. It is most industries in the northern part of Alberta, and the oil sand operations are concentrated in this region. So here you see the mean nitrate concentration. This picture shows, it doesn't show much here, but when you compare to this one, that is the maximum concentration in maximum nitrate concentration in shallow groundwaters of Alberta. And here is a spatial distribution of the deep water wells from 50 to 150 meter below ground level. It's a very less compared to the shallow wells, because then we can see that the agricultural activities are mostly concentrated on the superficial aquifers. So the impact from the agricultural activities will be more on the superficial aquifers. So that is why it is more in the shallow depths. So here you see the formation-wise nitrate concentration. So as you see here, 87 wells are in the post-Paleocene deposit, that is the superficial deposits, with a maximum concentration of 431. It is very high compared to the 45 milligram per liter. Similarly, the other formations also, and Scollard formation has the maximum, because the report says that the Scollard formation is the water, they are in connection with the, in some parts it is in connection with the superficial aquifers.
Lali,
Yes.
you have more some slides. It's like now it's, 22 minutes over. Can you find a few minutes to finish it?
Yeah, sure. So this is a distribution of nitrate concentration geologic formations. So this is another picturization. This is based on the concentration here. This is below detectable limit, and this is the detectable limit, that is from 0.89 to 45 milligram per liter, and this is over the maximum concentration. So you see the superficial aquifers has more impacted with the nitrate compared to the bedrock aquifers. So what should you do if nitrate and nitrate levels are high in the well water? So for infants and pregnant women, so it is, as I shown here, it is more advisable to test the water more frequently, like 1 or 2 times a year. Avoid drinking contaminated water during pregnant period, or for the infants, do not use water for making prepare the infant formula, and use another source, an alternative source for drinking purposes. But at the same time, you can use the same for other household purposes, except cooking and drinking. So, and what are the treatment options if you have higher levels of chloride in your well water? So the most common recommended methods are reverse osmosis and anion exchange. Next, you will see the fluoride in groundwaters of southern Alberta. So as we see, fluorine is an abundant element on Earth's crust. It is naturally present in air and water and soil. So from the natural sources of fluoride in groundwater is from the rock, is mainly from the rock types, and man-made activities like fertilizers, septic in the agriculture field, and septic and sewage systems also contribute to the fluoride levels in groundwater. So how fluoride gets into the body? So once we drink water, 99% of the absorbed fluoride may be localized. Absorbed fluoride may be localized in calcified tissues. In adults, 50 to 7.
Sorry, Miss Lally, please can you
Yes.
show the final, if is there any fluoride contamination in the Alberta areas, then we can go straight to the discussion.
Yes,
part
yes.
of.
Okay. This shows a table of over 14.6% of the fluoride content of the wells has 14.6% of the wells has fluoride content above the permissible limit, that is 1.5 milligram per liter. And this is a spatial distribution of fluoride in southern Alberta in the domestic wells. So it is mostly it's not much, but the levels in the close to the agricultural fields in here. So as you see, it is higher. The next slide I'll show you. So it goes up to 4.5 milligram per liter. It is a farmland actually. And this is from another table from a Farmstead study from a Farmstead well water. So here you can see this is also an agricultural area. So that means the impact of the agriculture in groundwater in terms of fluoride content. So it is 6.37 ppm. It is an older report actually. So these are some of the pictures of how fluoride affects the health. So when the fluoride content is less than the recommended limit of 1.5 milligram per liter, it causes dental caries, that is decay of the enamel. And when it is high, it again causes problems like depositing, replacing the calcium and depositing fluoride and causing like dental fluorosis. And it is an irreversible cause. Irreversible case, you cannot treat it. The next one is, so this is the recommended limit. Below the 0.8, it causes dental caries. So the optimal level is like 1.5 to 2.4 milligram per liter. And over, if it is over that level, no, the optimal is like from 0.8 to 1. So 1.5 to 2.4 is recommended for adults, but not for children, especially the teeth growing stage, the permanent tooth coming stage. So what are the treatment options? As I mentioned before, here it is reverse osmosis anion exchange. So coming to the summary, so we saw the water resources, what are the role of the water resources and groundwater allocation and major aquifers, sustainable development and quality maintenance, potential contaminating activities, as well as potential contaminants of concern. So this, with that, we come to the end of this presentation, and thank you.
Okay. Thank you so much for your presentation. Really, it's excellent presentation, and you explain in very brief way of the Alberta hydrogeological issues and the groundwater contaminations by the various sources. Really,
Okay.
I will appreciate for your effort and the very neat and lot of information you added in your presentations. Really, I hope all our colleagues are impressive on your presentation. So, thank you so much. But I would like to open the questions to everyone. I think from the colleagues and students, please, if anyone would like to ask any questions, please raise your hand. Any questions? Okay.
There is a question in the chat box. Can you read that? Like,
yes, I can notice. Yeah. Yes, Prof. I think I don't want to read everything. I would like to ask a few questions. I think from the chat box. I think the first questions is there any environmental remediation to reduce the nitrate concentration in groundwater?
Not like the environmental reduction activity. It is mostly done at the domestic level or drinking levels, because it is only causing trouble to the health concern for the drinking water. So mostly what it happens is, so we have these treatment options the people can install. There are so many companies, they install the reverse osmosis and those treatment with the built-in water circulation system. So in that way you can regulate the exposure to the nitrate levels, but it is not done on the environmental level. But especially from the, because what is the agriculture being the most contributor to nitrate and so on the groundwater. So the business side and the government is like controlling the use of nitrate bearing fertilizers, limiting whatever it is needed, not over fertilizing the land. So just by controlling it, you can regulate the water level, the concentration of nitrate in the groundwater.
Okay. I think your question is very perfect. Your answer is very good. Thank you so much. But I think from my side, I would like to ask a few questions. I think 2 questions. I hope you are a very good experience with so many years in the consultant work in Canada, but and also you did hope you company and they did a lot of research based on the groundwater quality and the hydrogeological aspect in the Canada, and I think the Alberta area. Hope we understand that Canada is experience extreme cold weathers.
Yes.
Just I want to know, during the seasonal weather changes like as winter and summer, already you mentioned in the summer, the winter it goes maximum minus 5 to 15 degree in Jan to February, you mentioned. Is
And it even
there,
goes, it even goes below in the, when
yes,
it is
30
like
to,
the cold
yes,
events, minus
yes,
50
minus
also I
30
have.
to 40, minus 30 to 40 degrees maximum in Alberta area. Because I got some experience when I was visited in Montreal last
Oh,
years.
okay. Great.
Uh,
Yeah.
so, is there much groundwater depletions during the changes of the climatical conditions in that Alberta area? Also, is there much quality differences, like groundwater quality differences before and after the winter period, other than the any industrial inputs, industrial contaminations?
I haven't come across any like reports like that. Actually, I am not sure whether it is extending that. I also need to explore. I'm sorry, I'm not able to answer the question correctly right now because uh, I also need to look into those ones actually.
Okay, okay, that's
Okay.
fine. But another one more thing, so small things. You mentioned, I think, the nitrate and the fluoride contaminations. I can notice
Yes,
your presentation. The nitrate contamination, it's more than 700 milligram per liter. Some of
exactly. Yeah.
the agricultural activities, but really
Mhm.
it's quite very high is
Mhm.
compared with the WHO standards.
Yes.
Other than the nitrate and fluoride, what are the major industrial activities in the Alberta area? Is there any other trace metal contaminations other than the agricultural activities?
There are like arsenic, there are like arsenic, lead, uranium contamination, etc. So the arsenic is mainly from the oil sand deposits. It is also the industrial waste, as well as the arsenic, as I mentioned before, the oil sand bearing formations outcrop in the Athabasca, along the Athabasca River. So Athabasca River actually has natural higher levels of naturally higher levels of arsenic from the exposure to the oil sand bearing deposits. So
Oh,
arsenic is another one, and there are cases with uranium and E. coli, a lot of things. E. coli is mainly from the anthropogenic causes actually, and the agricultural fields also.
okay. Thank you so
And
much. Yes.
thank you.
Okay, thank you so much.
Thank you,
Really, I
everyone.
appreciate your answer. Due to time concern, I would like to close these sessions. Really, I know it's around more than half 7 in India.
Okay,
Colleagues,
yeah.
I would really appreciate and thank you everyone here for your time and giving us such a great experience. If you have any more questions, please chat through the email or email to our colleague, Ms. Lali Anil. Thank you so much. Lindo, you can take over these sessions. Thank you so
Thank
much
you.
for this
Thank you,
opportunity.
ma'am. That was a wonderful talk, very lengthy and detailed that you have given all the
I'm
details.
sorry. Yeah, thank
Yeah,
you.
it's all right. I hope the students must have benefited. So that was
Yeah.
a good way to put it. Thank you so
Okay.
much. Now,
Thank you.
Dr. Saju, do you have anything to add?
Thank you. Yeah, thank you very much, Lali. That was a detail and very well presented with all the documents and all the detailed reports and everything. That's a wonderful one. Thank you. And
Thank
I would like to announce that like we got an talk on 1st and 2nd of December. We got 2 talks on 1st of December, almost the same time. And the second, we got another 5 talks from well experts all over the world. So please connect with the Zoom or through YouTube, and look forward to see you all at that time. Thanks, Lindo.
So we are going to wind up today's session. Let me take a while to thank our session chairs, Dr. Saju Menacheri, Dr. Lindo Alapad, and Professor Vetri Murugan for handling the session. And an instruction to the candidates, the feedback link is provided, kindly fill it. And we will be back on December 1st and 2nd of December with the continuation of the session. Thank you very much.